the Verified Software from Theory to Practice workshop and Isaac Newton Institute workshop. So I'm Peter O'Hearn, and I'm going to chair the first session. A few notes before we get started. So this is being recorded. If you want to ask questions, you can just speak up and your question will be recorded. There's also a chat feature, which you can see down the bottom. You can post questions and comments via chat. And I've been told that sometimes a line transcript shows at the bottom, and if it's distracting to you, you should be able to see a way to turn it off via a button. Okay, so to get started with the first talk, Véronique Cortier is a research director at l'INRIA, Nancy in France. She's done lots of work on security, including in particularly e-voting, and using techniques such as first-order logic and rewriting. She holds an ERC starting grant and also an INRIA Academy de Science Young Researcher Award, which she got, I think, in 2018. She's going to talk about verification of security protocols. Véronique, over to you.
Well, thank you very much for the introduction. So I'm going to share my screen. Okay, is it all good like this? Great. Okay, so indeed, I'm going to explain how formal methods can be useful in the context of security protocols. So I'll first start by explaining what are security protocols. So these are the everyday programs that you are actually using every day that aim at securing communication, and there are various goals depending on the context. So for example, TLS, so the lock on the internet that established secure communication channel is one famous example that I think Karthik, the next speaker, will elaborate a lot on later on. But you also use cryptographic protocols when you do payment or on your mobile phone to authenticate, or on pay-per-view devices, make sure you get your movie, but only once or only during 24 hours, depending on what the contract is. And one particular example of security protocols that I'm going to talk about, because it's one kind of security protocols that I really like for the moment, is a voting protocol. And we are developing one particular voting protocol in our team. Its name is Belenius. So last year it has been used in more than 1,000 elections with a total of 100,000 voters. So you can just use it as well if you want. If you need some election in academia or in an association or whatever, you can just use our online platform. The code is open source if you want to install your own server, or you can just use our platform. So it's not just useful, it's also aimed at securing votes. In which sense? In the sense that votes should remain confidential, and I'll elaborate on this later on, and also verifiable. So it's not because it's electronic that you should have to trust the system. As a voter, you should have a means to verify that your vote is counted and that the result corresponds to all the votes that have been cast by voters. And to achieve this, so I don't see you, so I can't do a poll to know how much among you already used electronic voting. But in most commercial solutions, at the end, you're just congratulations, you have voted, it has been counted, but you have no means to check that. In Belenius and in most academic solutions, one key component is the fact that the ballot box, so the electronic thing that contains all the ballots, is actually public. So typically a web page or a distributed file, even that would be even better. But so you can access the ballot box at any time. And moreover, all operations like the tally, so when you count the votes, are verifiable, so can be checked by everyone, even if you don't have any secrets. So in particular, if you don't have the decryption key, you can still count the votes yourself if you wish to. So how does it work? So as all security protocols, it uses some cryptography. And I'm going to present the two main building blocks. The first one is encryption. So I guess you all heard about public key encryption. So this is something we use in voting protocol. We assume that there is one public key, the public key of the election, that everyone will use to encrypt his vote. But no one has a secret key. Instead, the decryption key is split in several keys, exactly like in a bank. It's no single employee has a key to open the safe. It's typically, you need 3 keys or 2 keys to open a safe. So you can do this cryptographically. And actually, more precisely, what we use in cryptography is threshold decryption. So you have several trustees. Each trustee will compute a secret key. And then the n trustee will jointly compute the public key, such that any threshold t out of n suffices to decrypt. So you can then set your threshold as you wish, 2 out of 3, 5 out of 10, or 5 out of 7, depending on how much trustee you want and how much robustness you want to. So you still want to decrypt even if 1 or 2 trustees are missing, for example, or maybe more. And so we know to do this in cryptography for a long time, in such a way that really no one has the decryption key. It has been done in a distributive way. So the decryption key is never present on a single computer, neither during the key generation nor the decryption time, so that no one the key, the trustee only have some share. The second key component that I'm going to use that is maybe less known outside cryptography is zero-knowledge proof. So the ability to prove to someone that you know something, like a secret key, without revealing, of course, the secret key. So I'm not going to explain how it works, but the kind of things you can prove. So you can prove many, many statements, actually any polynomial statements. And 2 examples of useful statements that we're using in the context of voting is the fact that if you encrypt a message, so here it's a message M encrypted with some key K. So the message M is completely hidden by the encryption. And what you can prove is that M is equal to A or B without giving any insight on whether it is likely to be rather A or B. So you can prove that the plain text inside the encryption is either A or B or belongs to any finite set that you want. You can also prove that you decrypted correctly. So given a ciphertext and some plain text M, you can prove in zero knowledge that M is indeed the decryption of the ciphertext C without revealing the secret key that you use to decrypt. So this allows you to prove many things without revealing either your vote or your secret key. So then now I have enough building blocks to explain at least a simplified version of Belenius. So in Belenius, as I said, you have a public ballot box. So assume here that the election has started already and David arrived and wants to vote. So you can already have a look at the ballot box if he wants to, and he can see that there are already encrypted ballots. So here, for simplicity, I'm assuming that it's a referendum. So you vote either 0 or 1, 0 if you disagree, 1 if you agree. And so David can just see encrypted ballots on the ballot box. So on his own computer, he will select his own vote, either 0 or 1, and he will encrypt it with the public key of the election that is denoted here, PK of E. And as I explained earlier, so it's a threshold decryption, such that so there is one public key that is known to everyone, that everyone can use, but no one has a private key. The private key is shared among the authorities, so like among 10 authorities, and 7 authorities will be enough to decrypt. So David just takes the public key and with his computer encrypt his vote, 0 or 1. So on his host computer, he has his encrypted ballot that is denoted here VD with braces PK of E. He can see it on his own computer and he will send it to the ballot box, gets authenticated as David, and then the ballot is just added to the ballot box. And at any time, David can check that indeed his encrypted ballot is on the ballot box. So he can check that his encrypted ballot is there forever. So then what about the tally? because here there is a link. It's not very difficult to, at least the server knows very well to who each encrypted ballot belongs to. So it would be dangerous for the privacy of the vote to decrypt each ballot one by one, because if you do so, then you know exactly who voted for what. So this is not how the tally proceeds. The tally in Belenius use the fact that the encryption is homomorphic, meaning that if you multiply all the ballots, you get, so if you multiply all the encryption, you get the encryption of the sum. So there is no fancy crypto here, it's just due to the fact that G to the A times G to the B is equal to G to the A plus B. So this is very interesting because anyone can just multiply the ballots all together and compute the encryption of the sum of the votes. Well, it's the encryption of the result. So it's still encrypted, so you don't learn much. But what you can do now is that the authority will only decrypt this last ballot. So the authorities will only decrypt the result. And they will, of course, prove that they decrypted correctly. So then anyone can check that the result, the sum of the votes, indeed corresponds to all the ballots that are on the ballot box. Okay, so what do we have? We claim to have a protocol that preserve vote secrecy, assuming that at least a threshold of the authorities is trusted. And it's verifiable in the sense that David can check that his ballot is on the ballot box, and everyone can check that the result of the votes, the result of the election is indeed corresponds indeed to the ballot box. But how can we make sure that there is no attack? And this is where formal methods come into the play. So probably I don't need to convince this public that formal methods are useful. But in the case of security protocol, it's particularly interesting because with proofs and formal methods, you can detect attacks before protocols are implemented and distributed, because as soon as you have some version that is on the internet, it typically stays there forever. So for example, if you have a buggy TLS, for backward compatibility, you're going to have this buggy TLS for a long time. So it's better to verify before deploying. And it's now a current practice for many protocols to develop a formal proof together with the design of the protocol. So this is the case, for example, for TLS or 5G. And in the case of e-voting protocol, I was actually quite surprised to read that in Switzerland, it's even written black and white on a law requirement that for any deployment of an electronic voting protocols, so in some national, not national actually, but county election, then you need to provide both a symbolic and a cryptographic proof. And this is really what is written in the law. And what I can find quite fun is that it's really how done cryptographic and symbolic proofs in the law. So I'm going to explain what they mean by cryptographic and symbolic proofs. And actually here I will focus on symbolic proof and explain what it is and how we can do that. So how to analyze security protocols in general and voting protocols in particular. As in many verification contexts, there is two main steps. One is to model, try to define mathematically, formally what it means, what is an attacker, what is a protocol, what property you want to achieve, and then prove it, and prove it by hand, or better, try to have decidability results, and even better have tools to analyze protocols or your system. And so, as I briefly mentioned, there are two kinds of models, symbolic and computational ones. So the computational ones are closer to cryptography, but as I said, I'm going to talk about the symbolic ones. And there are many variants of symbolic models, but they have all in common the representation of message that I'm going to explain in the next slide. Maybe to start with, what is particular to security protocols? Why aren't we using any good formal models that exist already? So I would say that security protocols are, in some sense, quite easy because there are programs of a reasonable size, so that can be done by verification. But one particular difficulty is the fact that we want to prove them secure against any attacker that may read any message sent on the internet, that may even block them, and even more importantly, send new message, any message it can produce. Which means that if you want to see that as a transition system, for example, then that's a system that is infinitely branching at any point. At any point, the system can receive any message and needs to react depending on the message. So, and this is maybe one of the most difficulty here. So can we decide security of protocols? Well, there is no, I'm going to spoil. No, it's undecidable in general. It's easy to encode your favorite undecidable problem. So we cannot decide security, even like simple property like, is my secret secret? This is undecidable. We can recover decidability if we bound the number of sessions. Then it becomes co-NP complete. And so bounding the number of sessions, it means assuming that you play your protocol only a finite number of times. So you use, you go on the internet only 5 or 3 times on your life. Then you can show that your protocol remains secure. So it's good to find bugs, but not enough to have a real guarantee. So when we want to analyze a protocol for a non-bounded number of sessions, so no matter how many times it is used, we need to find a way. And so how we proceed. So first, as I was saying, there are many models, but all have in common the fact that messages are abstracted by terms, meaning that, so terms are label trees. And so typically agent names, keys, nonces, so random values are just abstracted by atomic values. And then cryptographic primitives like encryption, concatenation is a function symbol. And so for example, if we want to represent the encryption, the message that is the encryption over the key K of 2 components, the agent names A and some random nonces NA, then we'll represent it as a term, so label tree that is rooted by some symbol, an encryption, that has 2 sons. One is a key K, and the other one is another subtree that is labeled by some other symbols representing the concatenation or the pair, that has 2 sons, 1 atomic value for, say, that represent an agent names, and 1 atomic value that represent a random value NA. So the intuition is that we forget about the mathematical values, the fact that encryption is over groups and so on. We just keep the structure of the message. And that would be enough already to capture a lot of bugs. And then how to model an unbounded number of sessions. So if you take one step back, what the kind of thing we need to model is something like, okay, for any message I receive, any message X, if I receive the encryption of X over the key K, I need to answer with X, and maybe X in clear, or maybe X encrypted with something else. So this looks very much like first order logic. And actually, for example, for intruder, we can very easily encode what an attacker can do with just first order formula, which even horn clauses. For example, if we use a predicate I that represents the intruder knowledge, then we can say something like, for any X, for any Y, if the attacker knows X, if he knows Y, then he knows the encryption of X over Y. If he knows the encryption of X over Y, if he knows Y, then he knows X, if the encryption is symmetric. And we can add as many formulas as we want, depending on which ability we want to reflect from the attacker. And then for the protocol, if we think about voting, for example, then we need to say something, for example, like, yes, Peter, maybe I have like 5 minutes left.
Well, you have 10 minutes.
10 minutes, good.
But we're hoping for 10 minutes of questions. So if you're moving towards the wrap-up stage, that would be good. Okay. For protocol, the kind of behavior we need to model is, for example, when David arrives, he needs to encrypt his vote, V, with the public key of the encryption. So he needs to retrieve the public key of the encryption. Probably the server, the voting server will give him the public key of the encryption.
with some certificate. So the public key of the encryption, PKE, signed with some certificate. So if I want, and then David will just check the certificate and encrypt his vote with so his precious secret vote with the public key he has received. So we can model that with, again, with formula, saying that the attacker can know the public key of the election and the associated signature at any time. He just has to listen to the voting server. And then anytime he is able to forge some X and an associated certificate, so X that signs X, so any signature of X with the right certificate, then he will gain knowledge of the encryption of the vote V with some randomness, encrypted with the key X for which he was able to forge a certificate. So we hope that he will never be able to, the only X that can be used is the public key of the election, but maybe depending on the protocol, he can have other certificates and maybe he can send other keys to David. And so again, we have a first order formula to express this protocol rule. Okay, so then we're quite happy because we have modeled our attacker with a bunch of formulas. We have modeled our protocols with another set of formulas. So then we need to define what it means to be secure. So if we just aim at secrecy, just for simplicity, this is pretty easy too, because what we want to say is that the secret should not be deduced to the attacker. So it should be true that it should be true that the negation of the predicate holds. So what we want is that not of the attacker of secret holds. And then we have this whole set of formula. And what we want to know is we can derive a contradiction, hence the secret is not secret, or whether our set of formulas is consistent. So, well, bad news, it is still undecidable. And well, I warned you in the beginning, the problem is undecidable. So what's the point? So the point is that once we have translated the problem in first order formulas, and we can use a lot of techniques on automated deduction and proof to check whether we get a contradiction or not. And this is, for example, how the tool Proverif works. So this is a tool developed by Bruno Blanchet and also Vincent Cheval in Paris. And it implements a sound decision procedure that may not terminate, but it is correct in the sense that if it proves that something holds, then it's holds. But in some cases, it just doesn't terminate, or in some other cases, it just say, I don't want to conclude. And it is based on a resolution strategy that I'm going to explain in the next slide that works very well on protocols. And in particular, it has been applied to more than 100 protocols in the literature, including TLS, for example, 5G, and many others, and also voting protocols, in particular to fulfill the legal requirements of symbolic proofs. So the two main protocols that have been considered for deployment in Switzerland, which is the vote protocol and the protocol developed by CITEL, have been both analyzed with Proverif. So how does so just in one slide, what is the key ID of the Proverif tool? So it does resolution. So the idea is that your set of formulas, you will add more and more formulas that are logical consequences of the previous ones. And to make sure you don't add too many formulas, you proceed by selection. So as soon as you have two formulas, you can deduce, so for example, A implies C, and you know that B or D is true. Then you can deduce that, and if theta makes A and B equal, then you can deduce C theta or D theta, but you'll do so you'll add, so it's always true that C theta or D theta is true, but you'll consider this formula only if A has been selected, and if nothing is selected in the clause B or D. And this selection function is sound, meaning you're not missing something. You're considering enough clauses as soon as your selection function is a selection function, meaning that as soon as you always select only hypothesis. And here you can see that we are using a quite old theorem. And this is really like the basis of the of Proverif.
Véronique, we should look to finish in about a minute or so.
Okay. Okay, I'll squeeze the rest of my talk. Thank you. And so thanks to Proverif, we are able to prove security of Belenius, so in particular verifiability as soon as either as soon as the voting server is honest, or at least the one giving the voting rights. And we have privacy as expected, meaning as soon as the threshold of the authorities are honest. And so it's still a very lively subject, and maybe one subject that I'd like to present at least a bit is one limitation of Proverif that you can see from the model is that it doesn't perform very well as soon as you have some global state like counters or ballot box in our case, something that involves tables where you can add elements but also remove some of them. It doesn't work very well. So for example, if you consider this example where we have an agent B who is going to decrypt for you. So if receives the encryption of X over key, is going to decrypt it for you and send X in clear, but only once. So if you translate it as an on clauses, you'll say something, okay, as soon as the attacker has the encryption of X over key, the key K, then he knows X. And this only once has been lost here, meaning that you will, although the corresponding protocol is secure, I will never be able to prove that it is secure because I cannot tell I cannot tell to my proof system that this formula is true, but only once. And so we have developed a technique that I have no time to explain, but by playing with the clauses, we can actually modify Proverif so that we are able to solve this issue for a number of protocols. Some of them being voting protocols, but also many other protocols that do used in TPM, for example. And so I'm going to conclude to let more time for the questions. So the fun part, I think, of security protocol is that formal methods are interesting, and the other hand doesn't work just directly. So we really need to develop new techniques to analyze protocols, but they are all based on well-established techniques like time algebra, equational series, clauses, and resolution techniques I've just shown, so that we can derive decision procedures. And there are now quite, there are several mature tools, for example, Proverif, but also Tamarin, that are able to prove security protocols. And for voting protocols, for example, voting protocols really push these tools at their limits. So there is still a lot we need to do to be able to verify voting protocols as a whole. And so that's quite a nice topic.
Thank you for that. I think we only have 1 to 2 minutes for questions now. And there's several. I'm going to read one from the chat from Andrei Paksevich. Will using off-the-shelf TP-TP provers like E or Vampire make ProVerif, GSANSVerif more or less performant?
So I think, so the question is, why not use Vampire that already can handle first order logic very well, and why have a dedicated tool? So that's a good question. The first answer is that so Proverif is really crafted for protocols with a very specific resolution strategy that performs well. And at least at the time the last comparison were made, Proverif on that specific form of clauses perform better than Vampire. On the other hand, these tools have improved a lot over the last years. And so we are actually now stealing ideas from these tools, like, for example, to check if a clause is already implied by other ones. So we are stealing techniques from this field to plug them into ProVerif and get improvement. But the short answer is that yes, we could, but actually ProVerif is more efficient because finely tuned for security protocols.
So, okay, we're going to have to move on to the next speaker. So Véronique, thank you very much for the talk. And there's several other questions in the chat. So I think you can go to the chat to answer those. Okay?
Okay.
Okay, so thanks very much. I don't know what the protocol is online, but I'll say thank you. Right. So the next speaker is Karthikeyan Bhargavan from INRIA, who's going to speak about putting verified crypto to work in web browsers. So are you ready to go, Karthikeyan?
Yep, I am. I'm just trying to find the screen to share.
Verified crypto to work. Sounds good. Let's hear it.
Okay, let me see whether I can just, I don't know why it's not sharing my window just yet.
Mind you, I'm going to try to stop you around 20 minutes or 22 minutes in to leave time for questions. Okay?
That's fine. So I'm going to try to front load my my main point, so you can pause me at any point and hopefully that'll work. I'm still struggling to find my PowerPoint window in the Zoom thing. It's kind of weird. I would have expected to be on top.
I think people have found it's better to share the whole screen.
Okay. Anyway, I think you're seeing my slides now, hopefully. All right. Thank you so much, guys. I'm gonna tell you a little bit about what we've been doing in our group. Okay, so all of us do this. We go to a bank using a web browser, do things which are kind of sensitive and dangerous. And the reason we do it is because somebody tells us, click on the lock, it'll say that your connection is secure, so you can do this. And if you go deeper into the web browser and you see what exactly your browser is doing, if you use Firefox, you'll see that, well, it's actually using crypto algorithms in the heart. So like Véronique was already discussing, crypto algorithms used in many, many different situations, and in particular in your web browser, there's a bunch of these crypto algorithms being used for every connection that you make now. And if you try to see, well, what are these crypto algorithms? There's not so many. In the modern web, if you're using WhatsApp, using TLS, you're using your web browser and stuff, there's a few algorithms which will come up again and again. There's authenticated encryption algorithms like ASGCM, CHA-20, some hash functions, some elliptic curves, some signature schemes. Now, as we go forward in time, there's more and more of these interesting new crypto things that are being added to our palette. But you know, the things that you see on the slide, they are the ones that you typically are using on a daily basis. So what's interesting about this, I think this is an excellent topic for formal methods, is first of all, obviously, this is all crypto code deep inside your browser, protecting every connection. So it's by default security critical, okay? And it's also large. Actually, if you go look at like a TLS implementation like OpenSSL, you'll find that in fact, a majority of the code is not protocol code, it's actually crypto code. It's more a crypto library than a protocol library. I would say about 100,000 lines of code just for the algorithms shown on top without the plus things and without the mutants and CO things. And the other reason it's interesting for formal verification is that if you look at a very high level, all of these algorithms, all the code that is implementing this crypto is implementing a very nice mathematical spec. Some of these are somewhat sophisticated maths, like the stuff that Véronique was showing you, like homomorphic encryption. For the most part, it's not so sophisticated, even it's kind of classical math. But what's interesting is that these implementations also have some other considerations that you may not see in regular software verification, like side channel mitigations, that you want to prevent certain kinds of side channels. The other reason why this code is interesting, let's say for verification, is that if you take a network protocol like WireGuard or TLS or Signal, you'll find that in fact, the computational cost of these protocol stacks is dominated by crypto, typically by elliptic curve crypto, but it's dominated by crypto. So really making efficient implementations of these crypto algorithms for different platforms is a major concern. So here we have like this small group of things that we need, everybody needs for security. It's got nice mathematical specs, but also has heavy optimization needs. So this is kind of a very nice target, I find, for verified software. So let's look at how this kind of software is actually built. So Typically, you start from some kind of standard. So this is an RFC written from the IETF on the Cha-Cha 20 and Poly 1305 cryptographic primitives, which are standardized not so long ago. And you start from a document like this, you look inside it, you find some pseudocode, typically written in some kind of fake Python-like language. And you look at that and you say, okay, I can implement it because this is really an implementation guide, right? So you write a C implementation of it. And for something like Cha-Cha 20, you can write a C implementation in about 100 lines of code. It's not very big. And it's reasonably fast. It's designed to be fast. It runs in 4 to 9 cycles per byte on any machine. It's completely portable. It's okay. Okay, you can actually use this on a daily basis. But of course, this is not fast enough if you're downloading gigabits of information from a website. So what you're going to do is you're going to say, well, maybe I can get something faster. So on the laptop on which you're watching this, it probably has an Intel chip. It supports something called AVX2, which means it has SIMD. It supports SIMD parallelism. And if you see that, then you can say, you know what, I can do 8 Cha-Cha operations in parallel, and so I can use the whole 256-bit SIMD operations rather than 32 bits, and that will really speed up my code by 5 times. So that's what I want to use. But then a lot of you are actually going to be using the same connection on your phone. On your phone, you don't have Intel AVX2. Instead, you have ARM Neon, which allows you to do 4 operations in parallel, which gives you some speed up, but you certainly want to use that speed up. You don't want to have slow scalar code on your phone. And then you have a brand new server in your department, and you say, you know what, my server can do AVX5 and 2, which means 16 operations in parallel. It's the 10x speed up. So before you know it, you have like 1, 2, 3, 4, 5 versions of your implementation, maybe even more, depending on the variants of all of these CPUs. And just for the Cha-Cha 20 Poly 1305 crypto standard, you end up with about 20,000 lines of code. Most of it is in completely unreadable assembly, which makes it hard to audit, test, and maintain. Each variant is written by a different person using different idioms, even though a lot of the algorithms are quite similar. They look very different when you actually use the low-level assembly instructions to implement them. This is why we end up with 100,000 lines, or maybe even a couple of 100,000 lines of crypto code, even though we have a very few well-chosen modern crypto primitives. And now we are going to be in trouble, because how do we know that this code is correct? There could be, of course, classic things like buffer overflow. We are in assembly, so of course there could be, even in C, there could be this kind of issue. There could be timing leaks or various other kinds of side channels you might be worried about. Or there could be arithmetic bugs. You might just have gotten some calculation wrong when we are optimizing for one particular platform. So the answer, of course, for this particular community is we should formally verify this stuff, right? And there are lots of very exciting new research projects which actually target this problem. The basic idea is, rather than go straight from pseudocode to low-level code, let's take a step in between. Let's write a formal specification for this algorithm, which could be written in some language like Coq or F-star or EasyCrypt, some sort of high-level language. Then we take the low-level implementation, which might be in C or in some kind of assembly, and we prove it to be correct. We prove it to be memory safe, we prove it to be functionally correct, and we also prove certain kinds of side channel guarantees at this low-level code. Now, this kind of thing can be done in various different ways. Some tools say, you know what, let's take the hardest and most interesting problem here, which is, say, the field arithmetic that is used, big number arithmetic that is used in many of these primitives, and let's just target that and build completely automated tools for it. And this is what Fiat Crypto does, and I think you'll hear more about that tomorrow. Some other approaches say, you know what, it's not enough to just verify the small subroutines. Let's try to verify whole implementations. Some of them do it in assembly, like Jasmine and Rail. Some of them do it in C, like VST, Hacklestar, SAW, and so on. And some other tools target other languages. But typically, a lot of these crypto things are either written in C or assembly. So a lot of these tools are targeting either C or assembly. So yeah, so you can take a single crypto implementation, verify it against a spec. That many tools are available for this, right? So let's accept that one implementation verification problem is kind of solved. We can talk more about it in the question area. So what is the next challenge? The challenge is, well, how now you verified this nice crypto algorithm. How do you deploy this, right? How do you go from theory to practice? There's two kinds of strategies you can follow. One, which most projects follow, is to say, what we're going to do is we're going to provide you with standalone, easy to integrate implementations, either as a C file or an assembly file. You can just download it and include it inside your application, inside your crypto library, and so on. And this is very convenient for some applications. It's very convenient for researchers, because for my research project, maybe I just want to show off my tool. I'm going to implement one algorithm like SHA-2 or one algorithm like Cha-Cha Poly, and I've got my paper, and I'm going to produce this this file which people can download and use. It's excellent for us. On the other hand, for most other users, probably it's going to be more useful to actually have a complete verified cryptographic provider, which is a full library, which verifies all the algorithms I'm going to need, so that there is no confusion about how am I going to compose this algorithm, which is verified, with this other algorithm, which is not verified. I just verify all the algorithms I need in one complete box. I put some nice APIs around it, which are nice and defensive, maybe make wrappers for different languages so people can just download the whole library and use it. So these are two approaches. Both of them completely are justifiable and work, and we use both in HackleStar. Some people prefer the first, some people prefer to use the second. But in both these cases, there are some challenges you have to overcome if you want your code to be actually used by practitioners. Because the practitioners who are actually going to integrate your code are not verification experts. In fact, they might not even be cryptographers. So they are security sensitive developers, okay? That's the demographic who's going to take your code and use it. So here are 4 rules that I've come up with. There are, of course, a lot more. This is completely subjective. The first is that your verified code usually must meet some predefined legacy APIs, because people want to take your code and use it directly with their existing system. They don't want you to tell them, no, you have to now completely rewrite your calls to the crypto so that all the buffers are independent or whatever it is. So they have some constraints that they are working with, and you have to produce code that meets those APIs. In particular, your code should not have some preconditions which are hard to enforce in the target language, like in assembly or in C, right? So, or it requires lots of checks dynamically, because that might slow code down. The second one, which is underappreciated, is that even though your code is verified, it should be readable and auditable. Because when we try to get our code into Mozilla Firefox, those guys actually want to audit the code, even though it's generated by a tool, and then they want to understand it, and only then will they accept it. The same kind of rules apply for the Linux kernel and so on. So if your code is not readable, even if you say, listen, I have a formal proof of this code, it's not really ideal, because people are not so likely to take your code and adopt it if they can't understand it. The third one, which may be obvious to a certain extent, but also it's a challenge for researchers, is that the verified code must be at least as fast as the unverified code that it replaces. So verification will get you a little bit of credit, but if you're slower than what was there before, especially since crypto is often a bottleneck in many of these systems, people are not going to be able to use this code. Okay, so that's be at least as fast as unverified code. And the fourth one, which is more of a should rather than a must, is that if possible, your code should support all the platforms that the user needs. Okay, and that's because if you don't, then you're basically adding one more implementation to the soup of implementations they already have, which only adds to the code complexity and maintainability. You're not reducing it. It's like the XKCD joke about one more thing that you're adding into the soup. And that's sort of not an ideal situation to be in. You may not even be sure when your verified code is actually being used if there are a bunch of other implementations that get triggered based on certain conditions. Okay, so these are the principles that we followed in trying to get HackleStar deployed in many places. So HackleStar is a verified crypto library. And the principle behind it is that we want to verify pretty much all the modern crypto algorithms that people need, and pretty much for all the platforms that they are running it. Okay, so you want it to be portable, but also portable in the sense that you want it to be optimized for each platform. So you want to verify everything if possible, okay, and provide nice APIs for it. That's the aim. I think we have gotten pretty far alongside this. So I'm going to focus on one angle of this, which is most recent work, which is an extension of HackleStar called HackleXN, which is now in HackleStar, but we call it HackleXN. And the idea is, well, how do you verify code for these different SIMD platforms? I have ARM Neon, Intel AVX2, Intel AVX5 and 2, and I also have the scalar code that I have to maintain for machines which don't have vectorization. How do I maintain all these implementations and verify them? Well, if you want this kind of method to scale, the only chance is if you can do your proofs generically and then generate code for all of these instances. So that's what we do. We write generic SIMD crypto code in the language called F-star, which some of you may have heard of. And it's generic in the sense that the code itself is parametric over the size of the vector. So the size of the vector could be size 1, which means it's scalar, or it could be size 4, size 8, size 16. It works for all sizes. So you write it in that style. And then at compile, and then you verify it generically once and for all sizes of vectors. And then at compile time, you specializes and compile it for each target architecture. In order to do the specialization and compilation, we rely heavily on the metaprogramming framework, which is built into F-star, the verified metaprogramming framework. And at the end of the compilation step, we generate C code for each platform. And the C code will use compiler intrinsics to be able to access the vectorization vector instructions for each platform. Okay, so that's how we generate all of this code. So what is the workflow like? Well, as we kind of started off before, we always start off from an RFC based high level formal specification written in F star. Usually for any RFC, you can write it in about 100 lines of F star. You can specify all the details of it. Then you write a generic vectorized spec, which is more like a low level spec that actually describes the algorithm you're going to use to implement this spec, but it is also an F star. And this can use a lot of SIMD patterns and libraries and lemmas that you have developed before. And you verify this once and for all. That this works for any length of vectors. This algorithm on the right implements the spec on the left. Once you've done that, then you write your low-level stateful code, which is going to actually do the array manipulations, make sure that you're not avoiding copies and all this kind of stuff. And you prove that your stateful code meets this low-level intermediate spec that you wrote. And you do this. This proves that your code is functionally correct, memory safe. It provides a property called secret independence, which is a kind of a constant time guarantee. And finally, once you've done this verification, you can compile your low-level code to both scalar code, which will work on any 32-bit machine, and vectorized code for different platforms. Okay, it just comes out, just spits out all these implementations. And the main manual effort here is actually on the left. So the right-hand side is more or less boilerplate. It works more or less standard. I mean, it can be sometimes time-consuming to debug stuff, but it's nothing spectacular. The interesting thing is in designing the algorithm for the vectorized algorithm and then proving that it's correct with respect to the high levels. And that's in fact the interesting part of the proof of stake. All of this is being done inside F star, which is a security-oriented language and verification framework. For those of you who don't know about F star, if you think of it as a programming language, it's like OCaml. If you think of it as a verification system, it's a bit like Coq. But the main difference is that it offers you proof automation via an SMT solver, which is a3. It has compilers, so it's really focused on being a programming language. It has compilers which will generate OCaml code, C code for a subset of F star or WebAssembly code. And of course, for the purposes of this kind of project, what's nice is that it also supports verified metaprogramming. It has a tactics framework, which is fairly new. And we really exercise all of these features in our system. So I encourage you to download it and play with it if you haven't already. Just to see how kind of give you a taste of what the verification steps look like in our framework. So let's try to look at this particular algorithm. It's actually one of the simpler algorithms in our system, but it's easy to explain. So this is SHA-2 hash function. At the heart of the SHA-2 hash function, there is a shuffling. Okay, you have 8 words, A, B, C, D, E, F, G, H, and you do a bunch of XORs, ANDs, and so on to shuffle these into get 8 output words, A, B, C, D, E, F, G, H. I say they are words because if you're using SHA-2 256 or 224, these are 32-bit values. If you use SHA-2 384 or 5 and 2, these are 64-bit values. So the size of the words depends on the variant of SHA-2 you're using. Okay, and this is one round of the compression function. So how do you specify this in F star? It's a high-level specification. So the first observation here is that we want to write a specification for all variants of SHA-2 at the same time, because we don't want to write 4 different specs for 4 different variants of SHA-2, because they really are doing the same mathematical operation. So for example, we can define in F star a word type, which is parametric over the variant of SHA-2. And depending on the variant of SHA-2, it's going to define word as either UN32 or UN64. So already we are now kind of beyond what things like OCaml can do, right? So this is really something that we need is a dependent type system like F star, Coq, and various other things to be able to write these kinds of specs. And then we can define our state as 8 words, an array of 8 words, okay? And this works for all SHA-2 variants. And then each of these shuffling functions we can define using some mathematical operations. For example, the CH operation takes 2 words. It basically does an bitwise AND, and does a bitwise XOR. And so this is basically one of the many functions that are used in SHA-2. You can write a sequence of these functions, and you can fully mathematically specify what SHA-2 does. But how do we, now next step is we're going to vectorize this. We're going to write an algorithm that does this a bit more efficiently. And the key idea in vectorizing SHA-2 is that SHA-2, since it's basically a hash function, it actually doesn't exhibit internal parallelism, but you can do multiple SHA-2s in parallel if you have a vectorized machine. So this is what you're going to do. You're going to take 4 different SHA-2 states. We're going to transpose them into an array of vectors. And then we're going to do the shuffling operation on each of these vectors so that it happens on all 4 states in parallel. And once you've finished all the shuffling that you want to do, you're going to inverse transpose and get back the 4 states that you wanted at the end. So this is going to be the strategy for running the same algorithm in parallel on 4 different states. Okay, and this is a very classic vectorization strategy. There's nothing super clever happening. But just to see what it looks like in F star, on the left is the original mathematical specification that we wrote. I'm calling it mathematical just because it's like for one instance of SHA-2. SHA-2 itself is not so mathematical, so to speak. And on the right is basically the generalized vectorized specification. And what you'll see is that basically what you're going to do is take every word and you're going to transform it into a vectorized word, which is going to be a vector of words, basically, of a certain width. And the width is we are parametric over the width. So right now here, I'm showing you 4 common widths that we commonly use, 1, 2, 4, and 8. But I could add 16, 32, whatever I want to over here, and it's still okay. Generally, I can define this for any width. And the vectorized state is basically an array of vectorized words. Okay, so that's the first step that you have to do. The second step is you replace all your scalar operations with SIMD operations. And for SHA-2, this looks quite nice because it's very trivial. I just take every scalar operation on the left and I replace it with the corresponding parallel operation on the right. So the spec looks more or less identical, except the operators have just been switched. And the AND operator on the right works for any width. So it's actually parametric over the width of the vector as well. And once you've done that, the last step is basically going to be to prove that the spec on the right implements the spec on the left, which means if I take W input states, I transpose them to get a vectorized state. I apply the algorithm on the right and I inverse transpose it back. Then I'm going to get basically the SHA-2 operation on each of those input states. Okay, so it's a classic sort of, you want to show that it commutes the diagram. So that's basically what we do for SHA-2. And of course, it's for each algorithm, the strategy is somewhat different. So Blake 2 has a different strategy, SHA-20 and Poly 135. Each of them uses a different vectorization strategy, but we have vectorized about 8 algorithms of this kind for 5 different targets. Some of these are the first vectorized implementations of any kind, and some of them are the first verified vectorized implementations of that kind. And the benefit of this methodology, of course, is that in the end, you get 24 implementations, but you only verified 4. Okay, so you verified them as generically as possible, but you've actually obtained lots of verified code, which we believe is good for both maintainability and, of course, scaling of your verification. And yes, you also get access to a whole bunch of verified patterns that you can reuse in doing new vectorized implementations.
So we've got 8 minutes left, and I'd like to have some time for questions, but
okay,
I'll
wrap up in a minute. So of course, the big benefit of all of the SIMD stuff is performance. So it's worth asking what the performance gain is. It's as expected. You get lots of 4 to 5x on AVX2, 7 to 10x on 5 and 2, and so on. So you get pretty good performance improvement over scalar code. There is still a gap with assembly code. So if you really hand tune assembly for a particular vectorized platform for a particular algorithm, you can still get 3 to 5% more speed than what our generic vectorization strategies are doing. Okay. So you might ask, well, can we close this last piece of gap? Now, in most cases, you don't care about 3 to 5%. Okay? But if you do, then yes, you can, because in our world, what we do is, okay, suppose we look at, if we find a particular routine like multiplication, which really would do much better if we could use some platform specific instructions, like on Intel, there's something called ADX, that you want to use those ones, and you really have to use assembly to do that. You can do that. You can write the whale code, which is verified assembly code, which is written on the right, verify it against the same specifications as the F-star code in Hackle-Star, and then integrate them back. And this is what the Evercrypt provider does. It takes some verified assembly code from Whale, verified C code from Hackle-Star, both verified against the same spec, and composes them to obtain verified mixed hybrid implementations. And doing that, you can actually basically beat all the performance out there. For example, here is an example for the curve 25519 elliptic curve, which is used very widely now. So if you use the portable Hackle-Star code, you're already pretty good. You're actually pretty fast. But if you use the mixed assembly C code, which are both independently verified but verified in F-star against common specs, you can get best in class performance. And the same is true for many other algorithms. All right, so Hackle-Star, this is I give you a quick tour through how we structure our stuff. It's widely deployed now, et cetera, et cetera. You can download it, you can play with it, you can extend it, you can help us out. And conclusion, I've presented a verified crypto library called HackleStar. It provides right now all the crypto needed for TLS, signal, noise, WireGuard, and so on, and for multiple architectures. There are many ongoing extensions and projects, for example, post-quantum crypto. How do you specify this kind of crypto software in Rust, and how do you link with Rust code? And how do you extend go up from crypto to go to protocol code like signal and noise and so on? So lots of interesting projects there. And lots of open problems as well. There's a very active area, lots of people are working on it, but we still don't have a very good understanding of how to provide protections against large classes of side channel attacks, including microarchitectural attacks. There are some new ideas, but we still don't, and it's not a solved problem. And of course, the big problem for the whole area, I think it's for the whole workshop, is how do you verify code written by non-verification experts? And we don't really have a very good answer for that. So I'm going to stop there and take questions.
Okay, great. There's a question in the chat. I'll just read it unless Adam wants to come on. Adam Schlipala says, the example on screen as I take this is parameterized over a finite set of SHA2 variants. Can you also handle infinite families of algorithm variants?
Infinite families of algorithm variants. Well,
can you be prepared for any bit with imagining a million years from now we might have trillion-bit integers? Can you prove now that it'll work?
Yes, so we do have type classes in FStar too, so we can actually characterize the set of bits or the set of variants using some. You have to provide me some set of functions and some set of lemmas, and then I can define the algorithm based on the underlying field description or machine description or variant description. And yes, we do often write proofs like that as well.
Does that require compile time case split over all instances of the type class? Like, for instance, are you depending on fixed width bit vector reasoning to make these proofs go through?
Not for the proofs. In fact, the proofs are easier if you're more generic. But when you are actually generating the code, yeah, you do need to kind of specialize it for specific instances. So the 4 instances I showed you, they are the ones for which we actually run the compiler to specialize the code out to. Because for them, we know that we have the underlying machine instructions that we can instantiate them with. For arbitrary sized ones, we wouldn't know how to compile them. So we would just sort of say, it would compile to C, but then the C would be unusable.
Okay, thanks.
Does anybody else have a question before I go in? Oh, there's a few from Leonard Beringer. Have you connected any code verification proofs to, it's moving, to proofs of semantic crypto properties in e.g. EasyCrypt?
Right, so we haven't linked FStar proofs like the HackleStar proofs here to EasyCrypt. The Jasmine guys though do have a way of verifying assembly code for correctness and then linking it to semantic security proofs in EasyCrypt. What we do here, there are 2 different projects that we can link our functional correctness proofs to security proofs here. One is the METLS project, the Everest project, where the proofs are linked to computational crypto proofs, which are done in FStar. And that's one methodology. This is called modular code-based verification of the code. And that is being done in the METLS project. And a different strategy is something I call DY-Star, which is between a collaboration between me and Ralph Kirsters and others at University of Stuttgart, where we link this to symbolic verification, like the style that Véronique was showing in the previous code. So we link the verified crypto code here to symbolic proofs of protocols in this other project. So there's one on computational, one on symbolic.
So there's a number of questions. You're not going to be able to answer them all. You're going to have to go to the chat later. From Michael Conard, was I correct in my understanding that FStar can actually synthesize C code, or does the user take the verification output and implement accordingly?
No, the FStar, there's a subset of FStar, which is called low star, which reflects the C memory model inside FStar using a particular monadic style. It uses an special effect for this. And code written in low star, which is where we write our right-hand side of the picture I showed you before, compiles to C. It also compiles to WebAssembly, and it also compiles to C.
Okay, there's 2 good questions from Mohammed Sardar and Peter Sewell. I'll ask the one from Peter because Mohammed's will take longer to answer. So you can do that later. So how much of the vector ISAs are you using here? Is good validation of your semantics for those an issue?
It is. Often, in fact, when we find bugs in our implementation or somebody else finds bugs by a fuzzing or something, is because we probably misunderstood some ISA instruction. That's a very common error, typically for some variant that we were not very aware of, like IBMZ or something like that. But it is an issue, and validation of this is an issue. the part of the ISAs we are using is actually very limited because we're only doing, essentially we're doing mathematical operations here. And we are limiting ourselves in our methodology to the things which are in common between ARM and Intel and so on. So we don't try to use extremely exotic operations which are not available on all platforms because that breaks our generic proof strategy. We could, and we do in some cases, so if the performance gains us so much.
So the deployed code, if there needs a patch, do the people have to come back to you to change it, or will they change it? Say Firefox, will they change it, or do they need to come back to you?
So it depends on the level of comfort for these developers. So for example, Jason Donenfeld, who maintains the code from both our project and Fiat in the Linux kernel, he's very comfortable changing the code himself. It doesn't mean that he's not going to make errors when doing this, right? So, but you know, some people are comfortable just editing the code and they don't come back to us at all. The Mozilla group, for example, they run CI. So they run verification as part of their CI. Yeah. And every time they generate the code and check that it hasn't changed. And if it has changed, then they raise an issue, it goes into the bug tracker, and then somebody has to respond to it, and typically it filters back to us. So typically, yes, we do have to get involved.
Okay, so thanks very much for this fascinating talk. Like I said, there's an interesting question from Mohammed Sardar in the chat.
I'll go to the chat and answer that.
Okay, great, so thanks very much. Okay, now we're moving on to the next talk. The next speaker is Justin Su, who right now is at University of Wisconsin-Madison and who will be moving to Cornell this summer. So Justin is speaking about his favorite topic, I think, which is learning something about probabilistic programs. So it's all, probabilistic is in there, Jason, as expected. Or Justin, pardon me. Over to you.
Yes. Thanks a lot, Peter. Yeah, so thanks for inviting me to this workshop. So I think the last few talks we've heard about a lot of interesting applications of probabilistic programs. In my talk, I want to kind of step back a bit and try to present some new techniques we've been working on to verify probabilistic programs of many kinds. So first of all, this is joint work with three great collaborators, my student Jalu Bao at Madison, Drashti Pathak, and Subhajit Roy, IIT Kanpur. So as we've seen in the last few talks, there's many applications of probabilistic programs. So these are programs that have random sampling. So we saw some good applications in crypto. There's also applications in privacy and machine learning. For the most part, these programs have been studied for quite a long time. So their semantics is kind of fairly well understood, but verification remains kind of difficult still. So there's been a lot of work on kind of automated methods that definitely Marta will talk about. These work very well for kind of simpler models of probabilistic programs like probabilistic automata, but they don't work so well for kind of more richer models of programs like probabilistic imperative programs or maybe probabilistic functional programs. So this is kind of verifying these maybe more realistic or richer probabilistic programs is kind of an active area of research. So the challenge I want to focus on today in specific is for loops. So specifically probabilistic loops. So these are loops where kind of the loop guard might depend on random samples, and as a result, a loop might run for a random number of iterations. So these can show up once in a while when you're analyzing certain kinds of probabilistic programs, and they can be hard to reason about. Sorry, distracted by the chat. So for instance, you can't just kind of unroll the loop because there might be a random number of iterations. And like always, when reasoning about loops, we would like some kind of loop invariant, but finding the loop invariant can be quite difficult or require a lot of human insight. So in this talk, I want to kind of talk about our work, kind of combining two kind of very well-known methods. The first is called weakest pre-expectations, and the second is kind of data-driven invariant learning. And we want to combine these two ideas to develop invariant learning methods for probabilistic programs. So if you haven't heard about either of these two things at the top, don't worry. I want to first kind of go through these two kind of prerequisites, and I'll talk a little bit about how we combine these ideas to kind of make it easier to reason about probabilistic loops. Okay, so weakest pre-expectations. This is a quick review. So first, I want to introduce the class of programs that we're working with. So we have, of course, plain imperative programs. So hopefully this is not too surprising. This is without probabilistic behavior so far. So here, programs kind of transform states to other states. Here, I'll just assume for the talk that all programs are terminating, or that you have some other way of verifying that programs are terminating. This is also a well-studied problem. To consider probabilistic programs, we might want to add a kind of a sampling command to the language. So here I've added a flip command that will flip kind of a biased coin. Say it's going to return 1 with probability p and return 0 with probability 1 minus p, and it will store the result into a variable x. Okay, so it's the same kind of programming language with just one extra command for random sampling. Here we can think about programs that transform states to kind of distributions over states. So you plug in some input state, some input setting of the variables, and you'll get some probability distribution over the output. Okay, so for reasoning about these kind of programs, one kind of well-studied method is called kind of based on weakest pre-expectations. So the way this works is that the rough idea is that we want to generalize our typical binary predicates to real valued versions of predicates. So if I have a binary predicate, it maps every state to 0 or 1. Maybe 0 is kind of a bad state and 1 is a good state. And I want to generalize these kind of predicates to what are called expectations. So these are maps from states to real numbers. So you can kind of think about this as kind of a quantitative version of predicates. So this is kind of an old idea. It was first proposed by Dexter-Kozin and really developed a lot by Morgan and McIver in their work on pre-expectations. This is definitely not something we are proposing for the first time. I just want to give a sense of how you can use these kind of quantitative predicates to kind of prove properties about a probabilistic program. So you can use these expectations to kind of encode various quantities that are associated to your program. So for instance, if you care about the probability of some event, you can encode that with an expectation that says maybe this expectation E is going to be 0 if X is not equal to Y, and it's going to be 1 if X is equal to Y. And then by averaging this function E over the program outputs, which is a distribution, this will give you the probability of X being equal to Y. So you want to compute what is the probability of X equals Y in the output of your program. You can average this expectation, this kind of quantitative version of a predicate over the program output. So another kind of typical example was, say you care about the average running time of your program. Like I said, some of these probabilistic programs, maybe the running time depends on random sampling. You can say that maybe E is going to represent the running time of your program, T. So it's going to map every input state to how long this program is going to take. It's going to map every output state to how long the program has been running. And then averaging E over the program output will give you the kind of the average runtime of your program. Okay, so these kind of examples show that these quantitative expectations can model kind of quantities that you might care about for your probabilistic program. So if you want to analyze your probabilistic program, you want to reason about kind of these expectations. So in both of these cases, the kind of the key thing you want to do is you want to average E over the output of your program. Okay, so again, this is kind of still kind of difficult. We're kind of just transforming the problem into something else. But kind of work by Carol Morgan and Anna McIver developed this weakest pre-expectation framework. And the idea is that this is kind of a quantitative version of weakest preconditions for standard programs. So kind of if I'm given a probabilistic program C and an expectation E that I care about, then the weakest pre-expectation, I'm going to call WPE CE. This is defined to be the average of E over the output distribution. So as I showed on the previous slide, many quantities you might care about for your probabilistic program can be expressed as averages of E over the distribution. And the idea is that this kind of framework will let us simplify reasoning about these programs because computing an expected value in the output is maybe difficult. We can try to do the easier task of computing this weakest pre-expectation instead. Okay, so far this is just still a lot of definitions. So the main kind of insight behind this weakest pre-expectations is that for simple programs, this operation can be computed purely syntactically. So if you look at these rules, so these definitions, they look very similar to kind of Dijkstra's weakest preconditions. Perhaps the only different one is for handling kind of random sampling commands. Right? So for random sampling, roughly speaking, you kind of substitute the possible outcomes of the coin flip in for the expectation, and then you kind of average kind of take a convex combination. With probability P, you have the first thing, and with probability 1 minus P, you have the second thing. So for instance, if I have a program, this very small program here, that flips a coin and stores it into Z, and I care about this expectation 5 times Z, which is going to be 5 if Z is 1 and otherwise 0, then using kind of this highlighted green rule here, I can show that WPE of this program and also of this expectation is just 5 times P. So that shows that the expected value of 5 times Z is really 5 times P, which is what you might expect, because with probability P, you get 1, and with probability 1 minus P, you get 0. Okay, so I haven't showed anything about loops here, and as you might have expected, this picture is not going to be so simple for reasoning about looping programs. So it's difficult to kind of directly compute WP of a loop, because as usual, this thing is going to be defined in terms of a least fixed point. So we can't come with a kind of a clean expression or a simple expression about what exactly is expected value of E after the loop. We can't do this in all cases. So just like for weakest preconditions, it's going to be much easier if we have an invariant expectation I. So this is going to satisfy this kind of invariant condition. Again, the details aren't so important, but at a high level, this invariant expectation should satisfy some property of the loop body, which can be easier to check. And if you can establish this property, then you can show that this invariant expectation is actually equal to kind of this weakest pre-expectation. So the thing on the right is kind of harder to evaluate, but if we can find some invariant expectation I magically, and we can check the property on the left, then that suffices to kind of give us a handle on what this loop is doing. Okay. All right. So I'm going to give a quick example of just one program that we might want to analyze. So this is kind of a simple program for reasoning about biased coin flips and coin flips. So the idea is that I have two kind of 0, 1 variables, X and Y, and I'm given access to kind of a way to flip a biased coin. So I have a P biased coin, so you can imagine P is a quarter. I don't have a way to kind of flip a fair coin, but I can use this kind of simple probabilistic program to generate fair coin flips. So the idea is that as long as the two variables are equal, I'm going to flip both coins. And as soon as the two variables are not equal, I'm going to take, say, the first value, so the value of X. The rough idea is that when I've stopped this loop, either have 1, 0 or 0, 1, and these two events kind of have equal probability because the coins are symmetric. And then if I look at the first, maybe the value of X, I have equal chance of ending with 1 or ending with 0. So to use this kind of weakest pre-expectation framework, we can kind of try to prove that the expected value of X at the end of the program is going to be P. So that, sorry, it's going to be 1/2, which shows that it's going to be kind of a fair coin flip. So in terms of weakest pre-expectations, we want to show that WP of the fair program with the post-expectation X is going to be kind of this thing on the right. So this says that if X and Y are equal initially, that I enter the loop, and I have kind of 1/2 chance of having X equals 1 or X equals 0. Of course, if X and Y are not equal initially, then I don't enter the loop at all, and kind of the expected value of X is just going to be the initial value. That's the second component here. So kind of computing this thing directly is not straightforward. Kind of given this loop, there's no obvious way to come up with what this thing on the right should be. But if we have the thing on the right, we can kind of check that it is an invariant by checking this invariant condition here, the last bit on this slide. This part is much easier because there's no loops involved inside the loop body. Okay, so to kind of sum up where we are, we've talked about probabilistic loops. I want to say that finding an invariant is difficult, but can be very helpful for kind of proving properties about these loops. So the idea we want to take is that we want to borrow some ideas from kind of standard invariant learning in order to kind of find these invariants in a way that can be automated, where the user doesn't need to kind of magically come up with these loop invariants. So I want to kind of briefly overview this idea also. Again, we are definitely not proposing this, but I want to show you a little bit about how this works. So in standard invariant learning, we kind of forget about probabilistic programs for now. And the idea is that we want to find invariant predicates of programs, right? So these are conditions that always hold at a certain program point. So for instance, given a program, I might be curious, what are the conditions that always hold at the start of a loop, right? So we can use these predicates, these invariants, to kind of construct a loop invariant and make it easier to verify our standard program. So just for a simple instance, here's a simple loop. It's not probabilistic, but you can maybe say that one possible invariant is that x plus y is less than n as a loop entry. It's kind of preserved and turns out to be a true loop invariant. So the main insight behind data-driven invariant learning, such as tools such as DICON, and there's a lot of work on this, is that finding an invariant directly can be quite difficult if you look at just the program. So maybe we want to kind of counterintuitively just kind of ignore the whole program. So we want to treat the program as just a black box that we can run and observe outputs. And what we're going to do instead is that we're going to run the program on a lot of inputs and observe kind of traces of executions. So for instance, I might want to label reachable states 1 and other states, non-reachable states, I'll label 0. And I'm just going to kind of run the program kind of in a blind way on lots and lots of inputs. And by ignoring the program, I'm left with a bunch of trace data that goes through this program. And I can consider, invariant learning as kind of a classification problem. So I'm going to try to learn like a machine learning classifier to separate zeros and ones. This is a very well-studied task in standard machine learning. And the idea is that each learned classifier kind of corresponds to a candidate invariant. This might be an invariant of my program, or it might be something that's just a spurious invariant. But either way, I can try to use these invariants. I can present them to the user, and then the user can kind of verify the invariant property themselves. Right? So it will kind of suggest invariants for you by simply running the program a lot of times. Okay, so essentially we want to kind of borrow this idea to kind of learn our kind of probabilistic invariants for probabilistic programs. So I want to quickly sketch kind of how this works. So my problem setup is I'm kind of given a probabilistic loop while B do C, and I'm given some expectation E that I care about. So this might represent the running time. So if I want to care about expected running time, it might represent an indicator variable of some kind of event if I want to analyze what is the probability of this event at the end of the program. And I want to find an invariant expectation that will let me kind of bound the expected value of E. So the invariant condition looks something like this, like I showed before. It turns out that it's kind of tricky to directly cast this as a machine learning problem because the thing on the left mentions the invariant in kind of two places. So what we're going to kind of do is kind of learn this invariant in kind of a circuitous route. We're going to kind of sidestep this difficulty by, I'm just going to say, like, what happens if I try to learn this WP directly? Like, this is going to be the expected value of E after the loop. What happens if I can learn it directly? So of course, there are many cases where this is going to be very complicated and maybe I cannot learn it. But for many kind of simple programs, we can already get a lot of mileage by trying to learn this expected value directly. And upshot is that if we can learn this, this is an invariant. So we can kind of take what we learned and try to check to see if it's an invariant property to kind of verify that it actually is going to give me a correct bound on the expected value. So the main insight of my observation of our kind of work is that by kind of trying to learn this expectation, we move from what's typically a classification problem into a regression problem. So kind of the idea is that given some state S, input state, I want to predict the expected value of E in the output distribution after running C. So the idea is that my model should be producing numbers, kind of real value things, and not a binary yes or no, right? So I'm not trying to figure out if this state is reachable or not. I'm trying to say, given the state, what is the expected value of this thing? So it's going to be some quantity. So again, this is kind of a very standard and very well-studied problem in machine learning. So we can hope to borrow a lot of the ideas there in order to kind of turn them into this program analysis task. Okay. So there's still kind of the question about, what kind of model to learn, right? So there's many known kind of models for regression. Maybe the most example are kind of linear models. So for example, we might have models of the form alpha times X plus beta times Y, where X and Y are program variables. And the learning algorithm is going to take a bunch of data and try to find constants alpha and beta that fit the data. So this is kind of the first regression model that's often taught in machine learning classes. It's very simple, but it's a little bit limited because it doesn't support Boolean predicates, right? So you're not allowed to kind of branch on whether predicate is true or not in order to select which model you want. So this is actually quite useful that many of the invariants that we want to find do have these kind of Boolean branching. So we would like to support them inside the model. Otherwise, we cannot kind of find invariants. So our choice is going to use something a little bit more general, which are called model trees. So you can think about these as a generalization of decision trees for regression. So you have kind of a tree of predicates, Boolean predicates, and at each leaf, you have a linear model. Okay. So these are the things that we want to learn. These are kind of class of models. And again, there are existing kind of methods for learning these kind of things from data. So to kind of show a little example of a model tree, here I have drawn one model tree. I'm saying X and Y are numeric variables. And if I evaluate this model tree on X equals 1 and Y equals 1, I'm going to get 0.45. Right? So I start evaluating at the top. I say, is X equal to Y? It is equal to Y. So I follow the yes branch. Then I ask, is X equal to 0? X is not equal to 0. So I follow the no branch. And I end up at 0.45. So here the models, this model here is just kind of a constant number. But in general, it could be like a linear model that maybe takes some linear combination of X and Y and predicts a number. Okay, so these are the models we want to learn. And then to kind of give our kind of algorithm overview to put the pieces together, the inputs to the algorithm are going to be a probabilistic loop, while B do C. I'm also going to be given a target expectation that I care about. So I want to predict what is the average value of E in the output of the probabilistic program. And I have kind of 4 main steps that you do just like in data-driven invariant learning, right? So first, I'm going to run the probabilistic program on different inputs. A little twist here is that each run is only going to observe one output. So in order to kind of get good coverage of the distribution of the outputs or estimation, I'm going to have to run this probabilistic program on each input many, many times. So I can run this program many, many times. I can record data, I can build my data set. You can say in the first run, E is going to be this value, and I run it again, E is going to be this other value, and so on. The second step is once I have kind of my training set, I can use an off-the-shelf machine learning regression algorithm to learn these model trees from my data. Okay. The third step, which I'll talk about a bit more later, is that we want to repeat this many times in order to generate lots of model trees, and then we want to combine these model trees together to build one kind of average model tree. And then finally, I can kind of convert the final model trees into expectations and present them to the user. And the user can then kind of verify the invariant property, on these candidate invariants to figure out if they're actually correct or not. So since I'm trying to keep this talk kind of short, I'm not going to talk about the more boring steps. I'll just say a little bit about the third step, which is quite important. The issue is that kind of the learning process that we do is very noisy. So the training data is randomized, it's not deterministic. It's very easy to overfit the data, right? So our approach is kind of to learn multiple trees separately and then combine the trees using various heuristics. So this kind of reduces the variance of learning and helps avoid overfitting.
Justin, you're
yep.
8 minutes from the end. Probably it would be good to finish in 2 to 3 minutes.
Yep, that's right. Thanks a lot, Peter. So I want to say a little bit about implementation experiments. We implement this technique on a lot of weakest pre-expectation benchmarks to try to synthesize invariants. These benchmarks that we use kind of cannot be handled by existing techniques because they are involving kind of this Boolean branching condition, or previous techniques are maybe not fully automated that they might need the user to solve some kind of complex logical formula. But our tool doesn't need any of this. So you essentially just run the program a lot, try to fit a model, and then average the trees. I'll kind of skip over this kind of example here, just going back before. Just kind of wrapping up, there's a lot more in the paper that I didn't have time to cover. So, we kind of make a better connection invariants, discuss when we can expect to find an invariant using this method. We have a lot more on kind of combining trees. So, the general goal is kind of combine these trees together while preferring simple invariants. So this turns out to be an interesting problem as well. And we have some heuristics for handling more difficult benchmarks. Maybe the user can provide some guidance, so the base version of our technique does not need any kind of user-provided features. So I just want to conclude by 2 quick questions, kind of future directions. So the first question is that kind of we learn kind of these exact invariants, so somehow sidestepping the invariant condition. So one general question is how we can learn more general sub and super invariants, maybe when an exact invariant is difficult to find or very complicated. The second kind of more broader question is like, it seems to me that kind of using a regression for kind of these data-driven tasks seems to be an idea that's worth exploring. I'm not aware of prior work that does this, though there definitely might be some prior work out there. So I'd be interested in thinking about, are there other useful quantitative programming analysis tasks that could benefit from using regression instead of classification? And with that, that's all I have. Thanks a lot.
Okay, great. I'll leave it for a second. I've got a question. If nobody else puts one in there. So Justin, this idea of using, of learning the invariants, suppose we have non-probabilistic programs. Has that been shown to be very effective?
Yeah, so that's a really good question. So a lot of this work that, our inspiration for this came from kind of the existing work for learning invariants from kind of non-probabilistic programs. I think it's a little bit hard to gauge how, how useful it is, I suppose. There has been, many reports that it does seem to find invariants that are useful to people, though there's always a question about under what conditions can you be expected to learn the correct invariant. So many of these tools will just propose candidate invariants, but there's no guarantee that they'll find kind of the right thing. I think there's been some recent work, I think appearing at POPL this year, that tried to give better understanding of when these things actually work and try to give more theoretical understanding of, when can we find an invariant that is correct. But, when they can find invariants that kind of satisfy the condition, there can be quite useful because they allow the user to just verify a much simpler property instead of finding this invariant for themselves. So
I guess
so
what
you
I
might
was
be given,
is that to get started, you have to set up the language of predicates. So step one is choose the language of predicates, and then you can start guessing whether one of those predicates is an invariant. So this sounds like step one, make an abstract domain. And then, so I guess instead of employing a fixed point computation to find an invariant, you employ this other computation.
Right. Yeah, I think that's that is definitely right. So that is something that is a valid way of looking at it. I think my view on this is that kind of you do have to fix some predicates, but kind of the space of invariants that you can search are given by kind of the classification model that you choose. So you might use decision trees, you might use something else, but this is in principle a very broad class of invariants, and you don't have to bake in this very large class. Well, you have to assume that you're using this very large class, but then the algorithms that you're using to learn these models can be highly optimized, right? Because these classes are often very, very large. If you do something like naive enumeration, it will take you a very long time to find invariant in your class if it exists. But kind of by leveraging kind of more heuristics from machine learning, you can learn these classes much faster. So that's kind of my view on this.
So there's a question from Alejandro Aguirre, which is the invariant conditions inequality. Doesn't this mean that unless you manage to learn it exactly, you will fail to verify the condition?
That's right. So that is kind of this is what I was kind of alluding to with the first point here. So it's absolutely true that we kind of, by not using the invariant condition in some sense, we're not learning the invariant condition directly. We're trying to learn kind of this expected value directly. It is true that if that expression is very complicated, then this method will fail, right? So it may be that this expression cannot be captured inside the desired model, like this class of model trees. You might need something that's nonlinear and things like this. If that happens, then you're not able to do this. However, for many kind of programs that we consider, you're concerned with maybe the expected value of some variable. You can already kind of manage to express this in quite simple form. The only problem is that you don't know where the invariant comes from. So you need some kind of guidance or some insight about how to choose the invariant. Okay. But that's definitely a weakness of this approach that we're looking into kind of.
Majumdar, which is in the non-probabilistic case, there's the notion of ICE learning, where there are implication examples.
Yeah.
In addition to positive and negative. Do you also have an analog of this in the probabilistic world?
Right, so that's a good question too. We were inspired by ICE learning as we kind of moved on. So ICE learning tries to deal with the invariant condition more directly. And as we kind of moved on, we kind of felt that the correspondence between kind of classical invariance for standard programs and probabilistic invariance for probabilistic programs is actually not that close, right? So a lot of the, we get a lot of mileage from using this kind of weakest pre-expectation framework that kind of treats these things as if it was a weakest precondition. But there's many things about kind of standard invariance that don't translate so well to probabilistic invariance. It's not quite the same thing. So yeah, we are definitely looking to, can we design kind of a probabilistic version of ICE learning or IC learning? I believe that would help us kind of tackle this kind of invariant condition more directly. But so far, it's a little bit difficult. The main reason is that for a regression model, when you're collecting data, you want to say, here are my input states, and here's the output value that I want to predict. So if I have the expectation, I know the expectation from the user, I can simply compute that value E and kind of average it. And that's the kind of the ground truth about what I should be hitting. But if I have this invariant condition, then I have this kind of two-sided thing where I'm trying to learn a function or an invariant. Somehow the correct value of the invariant is itself a function of the invariant I. So I don't quite know what is the right number to shoot for in order to learn my invariant. So that's the main difficulty that prevents us from converting this into a regression problem. With a more general case, that we're still looking to how to attack maybe this problem more directly.
Okay, great. That's a good place to end. Thanks very much, Justin, for a fascinating talk.
Great, thanks a lot.
So now we've got a break, and people can hang around, or they can leave and come back. It's all good.
So I'm going to, I'm going to pause the recording and create some breakout rooms. Okay. So I'll assign the speakers, including Justin, to the individual breakout rooms, so you can continue the discussion there, and you can, you can yourself go to other breakout rooms if you want. So I'm going to pause the recording first, and then create some breakout rooms.
Okay.
So today I'd like to talk a bit about a recent theme of research that I've had along with a number of collaborators on robust program analysis. So the ideal picture of what a program analyzer does is that it takes a program and some property of interest and says, yes, this property holds, or no, it doesn't. But of course, all non-trivial questions about program dynamics are undecidable, and so the specification that's actually implemented by program analyzers looks more like this. There's a possibility that we return a definite yes/no answer, but we can also return an indefinite answer or just run forever. And so we actually have a very weak specification for what a program analyzer does. The program that just always returns unknown or enters an infinite loop is a perfectly valid program analyzer. It meets this spec. And the quality of an analyzer is determined experimentally. We run on a whole bunch of different tasks, and we say that an analyzer is good if it returns a definite answer often. And so for the past 50 years, we've developed some effective heuristic reasoning techniques that very often are able to provide definite answers to analysis questions. But unfortunately, they can be brittle and unpredictable. It's very difficult to tell what a program analyzer is going to do on any particular instance. And the specification doesn't tell us what to expect. So the situation is summarized nicely in this quote from a paper by Rustam Leno and Michael Moskal. Tools can understand our programs, but we cannot understand our tools. So I'm just going to go through a couple of anecdotes that illustrate the practical consequences of this lack of predictability. In the Iron Fleet distributed system in Daphne, the developers came up with information hiding techniques to circumvent inconsistent solver performance. So the performance of the solver was not robust enough for them to actually use it, and so they would prefer to just turn it off. A second instance is from the Coverity commercial bug finding tool, where they found that their customers really expected Coverity to have the same results from run to run, and as a result, Coverity avoids things like randomization, timeouts, theorem provers, out solvers, because these can all defeat that expectation that we have consistent results. So these were two instances where really the tolerance for inconsistency was very low, and users would actually prefer tools that are less functional but more consistent. So this raises the question of whether we can design program analyzers that to give us better specifications. So what are the useful specifications that a program analyzer might implement, and how do we design analyses that actually meet those specifications? And for this talk, I will concentrate on a particular class of specification, which I'll call robustness. And the idea is that we should be able to understand how a change to a program will impact its analysis. If I imagine that I have a program P and I transform it to P prime and analyze both P and P prime, I should be able to understand some sort of relationship between the information I compute for P and the information I compute for P prime. So there's a shift of perspective here from a program analyzer is a thing that acts on programs to a program analyzer is a thing that acts on programs and relationships between programs. As a case of particular interest, we have monotonicity, the idea that more information in means more information out. So if you imagine that a programmer has run a verification tool and found that a property they expected does not hold, they might modify their program by, say, inserting a missing method precondition, which increases the amount of information that's available to the program analyzer. And they expect that the information that the analysis computes is somehow better than from the untransformed program. So this is a very natural expectation, which is not met by many of the conventional program analysis techniques that we use today. So things like widening and abstract interpretation or counterexample guided abstraction refinement. These are non-monotone, and we need to come up with something new in order to meet this demand. So in the remainder of the talk, I'm going to develop a recipe for robust program analysis. And I'm going to develop it in the context of program summarization. So the idea is that I want a function that will take as input a program and produce a summary that over approximates its dynamics. So in the center of the slide here, we have a program on the left and a summary on the right. The summary takes the form of a transition formula, which is a logical formula that represents a binary relation on states. It's over two vocabularies. These unprimed variables represent the program state, or the program pre-state, and the prime variables represent the program post-state. So for example, since I is initialized to 0 and increases at every loop iteration, we know that the value of I in the post state must be greater than or equal to 0. And high is either decremented by 4 or remains fixed. So high in the post state is bounded above by high in the pre-state and below by high in the pre-state minus 4 times the number of times I took the loop. So I can use these summaries to, say, check specifications. So if I have some desired specification pre-post, then I can conjoin the precondition with the summary and the negation of the post condition with unprimed variables renamed to be prime variables and throw it to an SMT solver. If the result is unsat, then the specification is valid. And if the result is satisfiable, then I don't have any conclusion. This is an indefinite result because the summary is an over approximation of behavior. There are state pairs that belong to the summary that do not correspond to executions of the program, and we're okay with that sort of one-sided error. So the reason that I want to develop this recipe in the context of program summarization rather than the perhaps more familiar setting of state invariance is that I can compute summaries compositionally. And I'll first illustrate what I mean by that. So my summarization function is going to be defined by recursion on the syntax of the program. In the base case, we have an assignment. The transition formula for x gets e is x prime is equal to e, and all the other variables remain unchanged. If I have a conditional, then I'll compute a summary for each branch, conjoin with appropriate guards, and take the disjunction. If I have a sequential composition of P1 and P2, then I'll compute summaries for P1 and for P2, and then compute the relational composition. And if I have a loop, then I'll compute a summary for the body. I'll conjoin a guard. I'll compute the reflexive transitive closure, and then I'll conjoin with an exit condition. And so this last part was a bit of a lie, because we can't actually compute reflexive transitive closure of transition formulas. And so this sort of circled star is going to represent an over-approximate reflexive transitive closure operator. But all the other operations are just straightforward encodings of the meaning of the program into logic. There's no surprises here, which is great, because that means that the programmer has nothing to be surprised by. So beyond that, there's two reasons that I care about this style of compositionality. One is that it gives me a kind of locality property. So for instance, if my program is P1 sequenced with P2 and I change P1, that can't possibly affect the analysis of P2. The summary for P2 is a function of P2, not of the entire program, not of its context. So it gives me sort of a bound on the expected impact of a code change. The second reason I care is that the assumption of compositionality means that the summary for a loop is computed from a summary of the loop body. So regardless of how complex the loop body is, whether it contains nested loops or recursive procedure calls or whatever else, the loop analysis just gets to see this transition formula that represents an over-approximation of its dynamics. And the significance of this is that I can ask questions about the loop body summary that would be, and I can just pose those to say an SMT solver, that would be undecidable if I were to ask them about the original loop. So I'm doing some over approximation, and it allows me to choose an SMT solver to query the behavior of my loop body. And that's sort of the key that's going to allow me to achieve robustness specifications. Okay. So the missing piece of the puzzle now is that we need to have some way of over approximating the reflexive transitive closure of transition formulas. And the solution that I'm going to propose is very much in the spirit of this week at the Isaac Newton Institute. We're going to put theoretical models to work. So there's an active research community that's interested in models of computation that are weaker than Turing machines and which have decidable verification properties. And we're going to use those abstract models to summarize loops of real programs. The high-level recipe will look like this. First, we're going to synthesize a model of a transition formula, automatically, of course. Second, we're going to compute the exact reachability relation of the model. And third, we're going to translate that reachability relation into a summary for the loop. So the key here is that this second step is exact, which means that all of the abstraction happens in the first step, computing the model. So as long as we can make guarantees about the quality of our model, that will translate into robustness characteristics for the whole analysis. All right. Now I'm going to present this recipe in a little bit more detail. So I'm going to consider both transition formulas and my class of models as being instances of transition systems. So we just have some set of states and some binary transition relationship between states. The way that I'll connect transition formulas to their models is with simulations. Simulation from a transition system A to B is a map from the states of A to B such that transitions are preserved. So for every A transition from X to X prime, there's a corresponding B transition from S of X to X of X prime. Of course, there are more general classes of simulations that exist, but I'm going to stick with this very simple definition for the purposes of this talk. The key property of simulations that we're going to use is that if B simulates A, then the reflexive transitive closure of B's transition relation simulates the reflexive transitive closure of A. And so my refined recipe for how to define over-approximate transitive closure is that I'm going to compute the exact reachability relation of a simulating model, and then I compute the inverse image under the simulation. And that will be the way that I define my loop summarization operator. So let's look at what this looks like on a concrete example. So this is the example from a few slides ago, where we have a loop wherein the body I increment this I by 1, and at each step I increment either low by 4 or decrement high by 4. So I can imagine a state of this program as being a point in 3-dimensional space with 1 dimension for each of the variables. And I'm just going to trace through a couple of steps of execution. So if we start at the origin, then I can move into one of 2 states, depending on whether I increment high or decrement low. It's a non-deterministic machine. If I take another step, each of those states can transition to one of 2 states, and so on and so on. Now I'm going to take the image of this computation under a linear map. So I'm going to project the 3-dimensional space on a 2-dimensional space, where the first dimension corresponds to I, and the second dimension, Y, corresponds to the difference between high and low. And I'm going to retrace this execution, again, starting from the origin. If we take an additional step, then both successors of the origin collapse to a single state under the linear map. All 3 successors in the next step, again, collapse to a single one. And so we see that, in fact, the image of the transition formula under this linear map has very simple dynamics. It's just a translation. At every step, we increment x by 1, and we decrement y by 4. So the situation is that I have a transition formula and a translation, and I have a simulation between them that's a linear map. So understanding the iterated behavior of translations is easy. If I compose a translation with itself k times, that's the same as just scaling the translation vector by k. And then lastly, I'm just going to translate this back by taking the inverse image of this sort of closed form under the simulation, effectively just replacing x by I and y by high minus low. And I'll get this over approximation of the loop. So there exists some k greater than or equal to 0 representing the number of times I took the loop, such that I prime is I plus k, and the difference between high and low decreases by 4k.
Zach, you have about 5 minutes, give or take, and the audience can start adding questions to the chat.
Okay.
Go ahead.
So now we're in the situation where we know how to define loop summarization operators. Any simulating model gives us an over approximation of reflexive transitive closure, and we need to make a choice about which simulating model to use. So because we care about robustness, it's not sufficient to just choose an arbitrary model. We need to choose somehow a canonical or best model. So what does it mean to be a best model? And an answer to this question comes naturally if we formulate the problem in categorical terms. So if we imagine that we have a category of transition formulas where the objects are transition formulas, the arrows are simulations between them. And then we have a subcategory of models. So more concretely, you might think of the transition formula category as being transition formulas that are written in the language of linear integer arithmetic. The simulations are linear maps, and the models are linear translations. Then what we're after is a reflection of our transition formula F in the model subcategory. So this consists of a model along with a simulation from F to this model T, such that for any other simulating model U, there's a unique simulation from T to U that makes this diagram commute. So U is the composition of U bar and S. So in this situation, we'll say that S and T is a reflection of F. And if every transition formula has a reflection, we say that the models are a reflective subcategory. So this gives us our recipe for robust loop summarization. So we, as an analysis designer, we come up with a reflective subcategory of transition formulas, and then we define our loop summarization operator to be the one that computes a reflection of the transition formula within the model subcategory, computes the exact transitive closure of the model, and then takes the inverse image under the simulation. So the punchline is that any way that we design such a iteration operator, so for any choice of reflective subcategory, we arrive at an iteration operator that preserves simulations. So this is exactly the sort of robustness characteristics we were looking for. So if we have two transition formulas F and G and a simulation between them, then that simulation will also exist between F star and G star. And as a particular subcase, we have monotonicity. So if F entails G, then F star entails G star. And this is simply because F entails G if and only if the identity is a simulation between F and G. Moreover, we can show that any iteration operator that's defined in this way satisfies certain laws that can make it possible for a user to reason about how a change to their program might change their analysis, or it can also be used by a program analyzer to justify transformations. So these transformations could be performed by the analyzer in order to increase precision of the analysis. Over the last several years, I and my collaborators have developed a number of different instances of this recipe. So the different classes of models yield different types of abstractions of the dynamics of a loop, and you get different results that can be combined in various ways. One particular thing that I want to highlight here is that in recent work to be published at PLDI and CAB this year, we showed that this recipe can also be used to get robust termination analysis. And I'm going to present some experimental results for that. So this is the ESP termination competition. Compact is a tool that implements robust termination analysis based on linear dynamical systems. And we have a cactus plot here that shows the instances solved on the x-axis and time on the y-axis. And so the interesting thing to observe here is that that we don't actually lose anything when we gain these guarantees. So we don't return indefinite answers more often than the leading tools. It's roughly the same rate, sometimes better, sometimes worse, but we can provide these theoretical guarantees of robustness, compositionality, termination. And so to sum up, I think usability of program analysis tools is an underappreciated topic in the research community. There's really interesting theoretical questions to ask and answer there in terms of what kind of specifications are useful for end users and how to design analyses to achieve them. And within this little corner of robust loop summarization, there's lots of interesting open problems to be solved in terms of different types of models to explore, different types of simulations, different types of applications like property refutation or shape analysis. And so there's lots of interesting things to do. And that's it. Thanks.
Thank you, Zach. So yeah, please do add questions to the chat channel out here. We have a question from Madhu. Madhu?
Yeah, so maybe I don't understand it entirely, but the robustness looks too onerous to me. I mean, it looks like, if let's say I have a post condition and if I give a simpler post condition, you would expect that the loop invariant would be simpler, or the loop summary would be simpler because, you just need some property to prove the property that you want to prove. But seems to preclude that. Robustness seems to preclude that. Is that true? Or maybe I'm just getting it wrong?
Well, so I didn't really give a concrete definition of what robustness does. So I don't really claim that it's useful to say that any class of transformations that you could perform on programs would have a totally predictable impact on the analysis. I agree that that's too onerous. But something like monotonicity would be sort of a well-defined variation of what a robustness property is, where you pick a particular class of transformations and you say that those transformations have a predictable impact. So indeed, not every transformation has a predictable impact.
But in particular, if I make the condition simpler, the property that I want to prove about the program simpler, and I know it has a simpler loop invariant. Let's say X is even is all I want to prove, whereas I used to prove something much more specific about X before. Will robustness mean that I cannot create this? Still, I should look for this invariant, which is much more complex. It looks to me that it has to find the most complex for every specification possible.
I see. So by simpler, you mean in entailment order, not in terms of like the
yes. In entailment, it's like it has a simpler invariant to prove it correct. Then it seems to preclude it, because robustness would mean that you need to find the best invariant no matter what the specification would be, because you have to watch out, right? In that sense, it seems onerous to me, because my whole philosophy of program verification is that, according to the specification, the problem is to get simpler, right? So you're not doing exact reachability analysis.
Right. Yes. So this style of analysis that I'm doing makes the analysis independent of the property that you want to prove, and there are cases where you might not want to do that. So I think that this is partly a problem of robustness, but also a problem of compositionality. If you want your analysis to be compositional, it cannot be property dependent. And so there are lots of things that so I sort of agree that we're tying our hands behind our back by not allowing the analysis to be property dependent. But that doesn't mean that it's necessarily the wrong way forward.
That's fine. I just wanted to understand that it was.
Zach, I have a related question to that. I mean, you're trying to make the analysis referentially transparent, computational, but there are situations where, context matters. So for example, if you could propagate a constant, you could turn something from a nonlinear to a linear problem.
Yeah, that absolutely. So we're making our job harder by not allowing information to propagate, say, from the beginning of the program to the place where the analysis is performed. So what's surprising is that even though we are kind of tying our hands behind our backs in the sense, we actually don't lose anything experimentally compared with analyzers that throw every tip of the book at these problems. So indeed, we are making some problems harder, but we also have a significantly different style of reasoning that seems to be effective in practice.
So one way around this might be that if you could repeat the analysis kind of over and over, then you could actually build up a kind of assertional context so that you could use that the next time around to compositionally build a better approximation.
Yeah, that's true. You can imagine using such an analysis within a larger analysis framework that doesn't provide exactly the same guarantees, but would be more powerful in some sense.
So Martin Brain has a question here. Martin, you want to speak up? Yeah, the question is, how does this compare with strategy iteration approaches?
So strategy iteration is another class of techniques that give sort of completeness guarantees. So strategy iteration in particular has been used to show that exact interval analysis can be performed. So I guess some differences I would say is that strategy iteration works in the more standard state invariant style. It's non-compositional, and it has sort of a more limited class of invariants that it can compute. So the invariants that we compute using these frameworks involve disjunctions. They involve inequalities. Right? There's lots of this is a very expressive class of invariants that we're able to infer using these techniques. But the completeness results that are provided by strategy iteration, I think, are easier to understand for an end user. So if you say that the strategy iteration algorithm is going to compute the exact interval invariance at all points in the program, I think that the programmer has a really easy time understanding what that means. Whereas the kind of completeness results we get by saying that we're computing reflective abstractions, I think are not so easy to understand.
Hey, thanks a lot, Zach. Thank you. So can you stop sharing, and Jean-Francois can start? So while he's doing that, let me introduce Jean-Francois. He's a professor at the University of Brussels. He's interested in computer-aided verification and synthesis. During the last 10 years, he's concentrated his research on extending the theory of game graphs towards progress in reactive synthesis. He's been funded by the European Research Council for this project. I first met Jean-Francois at Mark Oberdorf, I think, in 1996. He was also kind of a star of the soccer team then, and it's one of the pleasures is watching people's careers develop over the years. And so Jean-Francois,
thanks a lot.
Yeah.
Thanks. So yeah, I will. So thanks the organizer for the invitation first. And so today I will report on some recent work that I did with students at ULB, Debrach Chakraborty and Damien Busato-Gaston, and two colleagues, Guillermo Perez and Shibashish Guha. So Guillermo is from Antwerpen and Shibashish is from Mumbai. So today I will speak about, how to combine some techniques coming from AI, and in particular Monte Carlo research, the Monte Carlo research algorithm, with techniques coming from formal verification. And I call this technique symbolic advice. So I will explain what and this is a contribution of this work. And so I will basically do that in the context of synthesis. So this is my primary research interest is the synthesis of control programs that are embedded in some environment, so reactive programs. And here the environment will be stochastic. And so I would like to synthesize a safe and hopefully efficient controller for the environment. And the challenge here will be that the MDP that I need to solve to obtain the controller is too large for exact analysis. So I will not be able to use my preferred probabilistic model checker to get the optimal solution. And what I will try to do instead is to so integrate techniques coming from AI that are usually scaling better than formal methods, but which are not getting a lot of guarantees with techniques from formal verification. And there are quite a lot of work in this direction for the moment in the field. Okay, and so my talk will not be technical, so I will try to give mostly examples of what we have done. And so I will use two applications for that. So I will use a scheduling application. And so the scheduling application will consist in scheduling hard and soft tasks. So hard tasks, you don't want to miss deadlines for them. So it's you really need to ensure 100% that the hard tasks are scheduled properly so that they do not miss their deadline. For soft tasks, you get a cost when you have a deadline miss. And so there is some stochasticity here because the arrival time for the task and also the computation requirements, they are drawn from some discrete distribution. So this is first, I would say, quite a serious application. And then I will consider a more funny application, which is to control Pac-Man in the famous game of Pac-Man and try to get the highest possible score. But both examples, so if you look at how to formalize them, so you will easily see that you can do that with a finite MDP, but the problem is that the MDP is very large. Okay, and so you cannot apply your favorite polynomial time algorithm to them because of the state explosion problem. And so here, all the challenge is to fight this state explosion problem. And to do that, so we will combine several IDs to do that. And so, as I said, those IDs are coming from artificial intelligence, but also from control theory. So in control theory, when you need to, synthesize a strategy to control a system, and you are not able to do it for the entire time horizon, so one way to maybe get a partial solution is to consider what they call receding horizon controller. So basically you fix a bound on the horizon, and then you try to compute a good or an optimal plan for this bound, and then you only play the first action. And then from there you observe what is the stochastic evolution of the system, and then you repeat this. Okay, but so the problem is maybe that even the bounded horizon that you need to optimize on is too difficult to solve precisely or exactly. And so one heuristic here is to use sampling techniques, Monte Carlo techniques, to try to get a good solution. Okay, and so, but usually for those techniques to work well, you need to insert, I would say, domain knowledge into the sampling search. And so this is the object of the contribution that we propose. So we will try to bring this knowledge using formal specifications, so to specify what are the promising area to look at. Okay, so this is the summary of the ingredients, but let's maybe go one by one into them in a bit more detail. So receding horizon control is quite intuitive. So you are in a state S with your Markov decision processes, and then, as I said, you fix some bounded horizon H, and then you look inside this bounded horizon for an optimal plan, or a good plan at least. And so what you do, so when you have this plan, you only play the first action, and then you observe what is the evolution of the system because of the stochasticity. I mean, you don't know exactly where the system will be after your first action. You observe, and then you get a new state S prime, and from there you repeat this process, right? So this is this sliding window that will go on, and then you repeat this forever. And hopefully, if your strategy that you compute on this horizon is H is large enough and representative enough of the future, then you will drive your system in a in a good way. Okay, but as I said, even computing this optimal plan for each step may be challenging, because so this triangle, so the unfolding of your MDP for the H next steps will be typically exponential in H, right? And so if it is too large, what you can try to do is to use sampling techniques. So, and one of the I mean, a nice algorithm for doing that is the Monte Carlo tree search algorithm. And so it is an algorithm that tries to search in promising subtrees, and hopefully it will get a good action to play at the root of the tree by only sampling a small subset of the branch of your tree. Okay, and the algorithm is organized in 4 phases that are repeated along the execution of the algorithm. And so there is a selection phase where, so if you have a subtree which is already developed, so what you will do is you will first try to look at either part of the tree that looks promising, or you will look at part of the tree that you have not explored yet. Okay, so there is this balance between exploration and exploitation. So you would like to explore the knowledge that you have gathered in previous iteration, but you would like also to make sure that you do not miss some good action by not exploring some subtrees. Okay, and so once you have selected a node, you expand your tree of one node, and then you want to get some information about this new node, and for that you use the simulation. So this is why this is called a Monte Carlo tree search. And so you will use there, I mean, either some very general strategy like a uniform strategy for looking at what is the value of this node, this new node, or you may want to use some heuristics that are given by some expertise in the domain. And once you have computed some value, V, an expectation of the value of the node, you can backtrack this information, and this will be useful for the next selection phase. Okay, and this algorithm, so it's an heuristic, but there are some interesting theory behind this. And so the theory, so it's trying to see how you can balance in an optimal way exploration and exploitation. And so for those that knows a bit about online learning, so this is based on multi-R bounded models. And the difficulty here is that you have drifting distribution, because I mean, the distribution are depending on the samplings that you are doing on the way. Okay, and so the advantage of those algorithms is that they are anytime algorithms. So you may say, okay, I have this budget, so I would like to consider a tree here which has, say, 100 nodes. Try to optimize the way you explore and exploit, and find for me a good action. Okay. And so there are some theoretical results and guarantees, but they are usually in the limit, so they are not very relevant, at least in practice. But so to obtain nice performances in this setting, so usually you really need to inject expert knowledge, and this will be done in the way you explore the tree in the selection phase or in the simulation phase. And so there is a famous recent application of this algorithm with AlphaGo, where, I mean, basically they are using this as a building block, but this is supplemented by self-play and deep learning for, I mean, improving the search and the way the simulations are done. Okay, but so what we want to do in this work is to show how to use formal methods to bias the search in the Monte Carlo tree search, because, as I said, you really want to inject some domain knowledge, and the idea here is to try to inject domain knowledge using formal specification, and to enforce this knowledge in the search by using techniques coming from formal methods. And so the objective is really to try to give a flexible but rigorous way of biasing the search in the Monte Carlo tree search, which what we call symbolic advice. And symbolic advice, they are simple objects, so they are specification over finite words, which basically advise the algorithm to visit those part of the tree because they are the most promising one. And so we allow for specification that will enforce properties about the branches that are built during the selection phase, but also properties that are enforced during the simulation. So and so maybe so I will give you examples with the two applications that I sketched in the beginning, so that it becomes more concrete. So let's take again the application for scheduling. So as I said, we have a problem where we have hard tasks, and maybe you have a few hard tasks, and then we have soft tasks, and we want to make sure that the hard tasks are scheduled 100% of the time. And for the soft task, we would like a good scheduler in the sense that the average cost along the execution of the scheduler is kept minimal in mean. Okay. And so to do that, so what we can do, for example, is to so just concentrate on the hard task, compute, so using safety games, the most general scheduler that will ensure 100% that the hard task are scheduled on time, and then so give this as selection advice and simulation advice to the Monte Carlo tree search algorithm, which will then look inside the space of safe scheduler. It will look for a good one using the Monte Carlo approach. Okay, so another way, I mean, here it's still quite costly because so the safety game that you need to solve will be exponential in the size of in the number of hard tasks. So for those that knows about shielding, so this is an instance of the shielding approach of Bloom and co-authors. But what you can also do in this scheduling problem is to advise MCTS to use EDF for the hard task and then leave the Monte Carlo tree search schedule the soft task. Okay, and so we can maybe look at the kind of result that you can get with this approach. So first, so as I said, so I am interested in MDPs that are too large for model checking. So here are some examples that we have considered, and this is the size of the underlying MDP. And as you can expect, for the MDPs that are too large, I mean, the classical model checking approach here, so these performances are reported for the tool Storm, which is a state-of-the-art probabilistic model checker. So you will get timeouts for the most for systems that are large. Here is the number of yes.
5 minutes.
Sure. And then yeah, as I said, so there are two ways of advising the Monte Carlo tree search algorithm. And so the two ways here are getting you safe scheduler, while if you do not use those advices and you give, for example, a very large cost for the misses of hard tasks, then you do not avoid missing hard task in execution. So then we have also compared this with deep reinforcement learning, again in an unsafe fashion or using shielding, and yeah, so the result that we obtain are favorable for MCTS. And so maybe to finish with this table, you can see here that the value that we get here, so it's the mean cost of the scheduler, is systematically better when you give more freedom to the search that is performed by the MCTS algorithm. So for the other application, it's the Pacman application. So I can also post on the chat a link. So maybe I can do that during the questions where you can see videos of the algorithm playing again the ghosts. And so there the objective is to eat hopefully all the pills that are on the board in the maze, and for that you need to avoid the ghost. So one advice that you can give to Pacman is to avoid ghosts at all costs. But there the situation is less favorable because there is no winning strategy, because if the ghosts are completely adversarial, so you cannot hope to escape them. Okay, and so in practice they are stochastic. So I mean, in mean, you may be able to eat all the pills, but if you were playing against optimal ghosts, that you will not survive. So there is no hope to compute a most general safe strategy in this case, because it does not exist. But so what you can do is you fix a smaller horizon, and then you can try to be safe for this smaller horizon. For that, you can use QBF, right? And so we have implemented that. Then we can also now turn to the simulation phase. In the simulation, if you want to be relevant, basically you should simulate traces where you do not encounter ghosts, because this should be enforced by the QBF analysis. And anyway, if you encounter ghosts, you will lose. And so for that, what you should do is then sample the state space of your Markov process uniformly for the paths that are safe. So it's sampling safe path, but this could be quite difficult to do, because if the set of safe paths, so the event that represents safe path has low probability, then the sample that you will draw at random will most probably be not interesting for you, and so you should. And so you can so get rid of this problem by using a SAT-based uniform sampling, which has been developed recently. And so we have used this also in this application. And so when you do that, so this is the table that reports the result of our experiment. So this is the plain MCTS algorithm. And so you see that in this, so for this set of experiments, which are the small grid here. So it's difficult to stay alive because there are a lot of ghosts and the grid is small. Then the MCTS algorithm without advice gives 17% of place where you get to the end and eat all the pills. While if you give advices to the algorithm, as we did with with QBF and weighted SAT, then you get 85% of win. And so just for comparison, we have played a lot of games with the students, and so what we get is usually a winning rate which is very much lower than what you get with the MCTS algorithm with advice. Okay, and so we can also see that if we make the grid larger, in fact, in this problem, it's easier because it's easier to stay alive. And so there, the winning rate is 95%, while the MCTS algorithm is only winning a very few games, because usually it's not efficient enough to finish. So there is some limit on the number of steps that you can take here. Okay, so this is for the Pacman. And so in this non-technical presentation, so I wanted to introduce this notion of symbolic advice that can be used to inject in a rigorous and systematic way knowledge in the Monte Carlo tree search algorithm. So this allows us to improve quite vastly the performance of this algorithm in non-trivial application. And so for doing that, we are using a lot of techniques that have been developed in the field of formal verification or formal synthesis. So like safety games, QBF, or SAT-based uniform sampling. And so we are currently implementing a toolbox where you can, hopefully you will be able to write directly in LTL the advices. You will be able to model your MDP using high-level languages. So for that, we borrow the languages, which is a nice languages for specifying Markov decision processes. And then we are providing interfaces to all those efficient solvers. And so what we would like also to do in the future is to use this algorithm, not maybe in real time, but as a way to generate good strategies that can then be learned by a neural network, and so to be replayed in real time after the learning. Okay, so that's what I wanted to say today.
So thank you, Jean-Francois. So I'll ask a first question. So, you know, the symbolic advice, is it entirely heuristic, or is it, you know, enforced? In particular, can you give any guarantees?
Okay, so I mean, in the scheduling example, there we have guarantees because we synthesize the most general scheduler, and then using this information, we can enforce during the Monte Carlo tree search that only a safe path will be visited, and also all the information that will be gathered during simulation, they will be, I mean, information that are generated by execution that avoid that our tasks are not scheduled properly, right? So, I mean, the scheduler will be safe for the hard task, and then we have no guarantee on the efficiency for the soft task. But experimentally, you can see that it improves largely the performances that you can get without the advices. And also, if you compare with state-of-the-art deep Q learning techniques, it's also give much better results. So, for the Pac-Man example, there is no winning strategy to avoid the ghost, as I said, because so if the ghosts are purely adversarial, then they can always catch you if there are more than one. I mean, if there is only one ghost, there is a way to compute a safe strategy, which will always avoid being in contact with the ghost. But this is only for one ghost. When you have several, you cannot ensure safety. So it means that the QBF that we do in an online fashion, which looks at a limited horizon, will not guarantee that at some point it will not end in a state where you don't have any more a winning strategy to avoid the ghost. I mean, just simply because it does not exist. But still, I mean, helping the MCTS and the search with this, I mean, min-max game, if you like. I mean, there for a finite horizon, we are really trying to find a winning strategy to stay alive for each step. Then this helps a lot the algorithm to explore interesting part of the search space.
So when it isn't a game, you know, when you're not playing against an adversary, you know, you can use something like beam search to.
Okay, so the Pac-Man, so there the behavior of the ghost is specific. So it's a stochastic behavior. So if you look at, so what we did is we formalize, I mean, the way the ghosts are really playing in the game. So by so basically, so you have rules like if a ghost is in an intersection and it's a random ghost, then you will take so uniformly at random next step. And so there is also ghosts that are chasing the Pac-Man with high probability, and so this is modeled in the MDP. But if you want to enforce, I mean, our idea is to say to Pac-Man, okay, try to avoid at all costs getting in touch with the ghost. And so this, for this, we forget about the probabilistic model and we try to compute a winning strategy for a few steps, which avoids with certainty the ghost when it's possible. And so this helps to drive the Monte Carlo tree search in the right direction somehow.
So Madhu has a question. So he says the formal guarantee of the symbolic advice seems only to handle properties of the horizon. Is there a way to give advice on the entire space? For example, regions that are known to be traps, etc., in a reachability game, where an agent could otherwise get stuck.
Yes, that's right. I mean, but so for example, in the case of, so you can compute the most general scheduler and then advise the most general scheduler using this, using the notion of advice that we have. So this is what we do in the scheduling problem. So basically there you need only one step, right? So because if you have the most general strategy, for example, it's an inductive set. So if you give me a state in that set, I can tell you exactly what are the actions that are safe, and then you will inductively fall again. So if you play a safe action into that state again, and then I can give you the same advice from there. So so for safety property, so if you are able to compute a safe strategy using abstraction, or so in the case of the scheduling problem, you can use also EDF, which do not require any computation, right? So because you know that if your set of tasks is schedulable, then it will be schedulable by EDF. But this has also this inductive property, so which means that you do not need to go beyond one step, in fact, for those kind of properties. And the edge step are plenty enough.
Thank you very much. So you can, yeah, we can have Javier share the screen maybe. Thanks a lot, Professor.
Okay, thanks. So I will post this link to the video so you can look at the Pac-Man playing.
Okay, so let me introduce Javier. He's going to be talking about verifying almost sure termination of replicated systems. And so Javier is a professor of theoretical computer science at the Technical University of Munich. His main interest is in the verification of concurrent and distributed systems, in particular the verification of systems with an arbitrary number of processes. He's also done work on probabilistic model checking and on the foundations of program analysis. By the way, as I was looking up, Javier has an excellent Wikipedia page. So if you want more information on him, you can go look him up there. So Javier.
Okay, I hope you can hear me. I just switched to the good microphone. Let me tell you that I got my AstraZeneca shot yesterday, so I'm feeling a bit dizzy today. If I fall asleep in the middle of the talk, you know why. So I want to talk about verifying almost sure termination of replicated systems. And so what are replicated systems? It's probably the simplest formal model you can think of in order to describe swarms of identical finite state agents, like tiny sensors with only a few bits of memory, or in the area of computational biology, you can use this to model systems where the agents are molecules or cells. So as I said, it's kind of the simplest formalism you can think of. You just have a finite set of states, and then a finite set of multi-set rewriting transitions, for example, something like this, which tells you that if two agents in states Q1 and Q2 meet, they can interact, and then they will both move simultaneously to state Q3. So then a configuration of the system is just a multi-set of states, or if you want, just a vector telling you for each state how many agents you have in that state. Since all agents are identical, that's all that characterizes completely the configuration of the system. And what makes it the important thing is that you can define infinite sets of initial configurations. And of course, you need a formalism to define infinite sets. And you can use Pressburger arithmetic, or if you are not very familiar with that, think just of linear constraints. So you can, for example, say that every configuration where you have any number of agents in a state Q1 and 0 agents in a state Q2 is an initial configuration. So in fact, what this means is that you have an infinite family of systems which differ on the initial configuration of the agents and on the number of the agents. So you can also have arbitrarily many agents. So, and then we assume always that there is a stochastic scheduling. That means that which are the agents that interact next, that's defined stochastically. How exactly, it doesn't really matter. The analysis that I'm going to present works whenever the only assumption is that every transition that is enabled must have non-zero probability. Okay, but which is the probability assigned to each transition, that's not essential. So, and as I said, this can be used to model, usually, of course, abstractions of multi-threaded programs or population protocols, which is a very popular model right now in distributed computing, or just some randomized, for example, consensus algorithms. Those are the kind of systems you can model with this. And the property we are interested in is almost sure stable termination. And what does that mean? So imagine that you have two Pressburger sets pre and post of sets of configurations, okay? And what we want to know is whether all runs starting at configurations of pre eventually reach post. Sorry, I should say whether the runs starting at configurations of pre eventually reach post and stay there forever with probability 1, okay? So essentially, we want to know whether this property, this LTL property, the runs satisfying this LTL property have probability 1. And which are the typical properties of in practice that you can represent like this? So typical one is leader election, or whether the agents reach a consensus. And I want to give you an example. So this is a little protocol in order for these agents, which we are going to imagine that they are birds, for them to decide whether there are at least as many blue birds as red birds. So these are birds, but as you can see, they are blind because they have these glasses. So they are flying around randomly, and whenever two birds come close to each other, they can interact, right? And the rules according to which they interact are these 4 rules. So, well, first of all, there are 4 states. So, which graphically we are going to represent as the bird is blue or red, and it can also be large or small. Okay, and then the rules are 2 large birds of opposite colors become small and blue. So the idea is that they, in order to see whether there is a majority of bird or of red, of blue or of red, they can just they annihilate, so to speak, right? And then eventually, the idea is that eventually only large birds of the majority color will survive, and those large birds, they can convert the small birds to their color, right? And then actually you are also, this is not enough. If you think a little bit about it, you will see that you also need a rule in order to sort out ties. And that rule is that the small blue birds convert small red birds to blue. So let me just illustrate a possible run of the protocol. So these 2 large birds of opposite colors may interact, and then they become small and blue. And now, for example, this large red bird can convert the small blue bird to red. And then, for example, this large blue bird can turn this small red bird to blue. Now these 2 can interact, and they both become blue. And now everybody is blue, and nothing else can happen, actually. So the birds have reached a consensus, and they will stay in this consensus forever. And this is the right consensus because there was an initial majority of blue. So I don't know if you are convinced that this is going to work in all cases or not, but this is exactly the fact that we will reach always the right consensus with probability 1. This is what we are trying to prove automatically. So this will be this would be the description as a replicated system. We just have 4 states: large blue, large red, small blue, small red. We just have these 4 transitions: large blue, large red goes to a small blue, and so on. And we have infinitely many initial configurations. Initially, all birds are large, and they can be blue or red. So we have all these initial configurations. For example, this configuration here corresponds to 3 large bluebirds, 2 large redbirds. Good. So the stable termination proofs that you find, the manual ones that you find in papers, the observation you make is that they usually are structured in stages. And the stages are kinds of milestones telling you that the system has got now trapped in a smaller set of configurations. And then it gets trapped in an even smaller one, in an even smaller one, until it gets trapped in actually in post. Sorry, there is a typo there, in post. Okay, and then the methodology that I want to present just reflects this idea. It's something that we call stage graphs, okay, because of these stages. So imagine take 2 inductive sets of configurations, means close under reachability, okay, C and C prime. And this is just going to denote that C eventually gets trapped into C prime. So you should think of C prime as a subset of C, okay? And this is just telling you that runs starting anywhere in C eventually will visit C prime, and since C prime is inductive, they will get trapped there with probability 1, okay? And then the equivalent of, when we are trying to prove termination, we use ranking functions. Here you can also use ranking functions that we are going to call certificates, right? Certificates for C gets eventually trapped into C prime. These are just functions that assign to each configuration some natural number, such that if you are currently outside C prime, then it is possible to reach a configuration in C prime. Sorry, it's possible to reach another configuration that makes the function decrease. Okay, and then this is and notice that the difference is with the usual case is there exists. For the usual ranking functions, every successor has to decrease the ranking function. Here it is just sufficient to have some reachable configuration which decreases the ranking function. And it is easy to show that certificates certify, so that C will eventually get trapped in C prime if and only if there is a certificate for that. And let me, for later, introduce the notion of a K-step certificate. So here, in order to try to find a certificate, given a configuration C, you have to, in principle, this configuration C prime here could be arbitrarily far away from C, okay? But in a K-step certificate, you know that the configuration is within a K, a circle of radius K. Okay, that's how far away you have to look from C in order to find C prime. Good, so then now we have all we need in order to define a stage graph for a given property. Pre goes to FG post, right? This is a finite directed acyclic graph whose nodes, which we call stages, right? They are inductive sets of configurations. So every stage is close under reachability, okay? Then pre is going to be contained in the initial stage. So you have here the initial stage, and then pre is inside it, okay? So now for every non-terminal stage, non-terminal means that it has children, right? Let's say, for example, 2 children. Then there is going to be a certificate telling you that if you start here, then eventually with probability 1, you are going to reach either this or that. And since they are close under reachability, you will stay in one of the 2 forever, right? So in fact, another way of visualizing this is assuming that this is C, and then that you have C1 here and C2 there, right? And eventually you will get trapped in 1. Okay, and then finally, every terminal stage, every stage without children is contained in post. Good. Let me show you an example of a stage graph for the majority protocol. We don't have to look into the details, but this is a stage graph telling you this is notation for the number of large bluebirds, right? So let's show that if we start with configuration, an initial configuration where the number of blue birds is smaller than the number of red birds, then eventually all birds will become blue, right? So your initial stage is going to be just this, because this turns out to be an inductive set. And then this is going to be the certificate. The certificate is the number of large birds. And you can show that, okay, this certificate proves that eventually the number of large blue birds will be 0. And then you are going to have another, and then this other certificate proves that eventually the number of red birds, the number of blue birds is 0. The stage graph for the case in which the number of blue birds is at least the number of red birds is a little bit more complicated. So for example, you see here that if I take this set of configurations, this will not be inductive. So then I have to find the inductive set, the right inductive set. And then, as you can see, the only thing I will guarantee is that if I start here, then this certificate is going to tell me that eventually I will be here or there in one of the three. Okay, and if I reach this one, where, as you can see, the number of large red birds is 0, and there is at least one large blue bird, then this certificate is going to guarantee that I will eventually reach that. Okay, so the question now is, how do we compute things like this automatically? Okay. First, there is a soundness and completeness theorem, which is very easy to prove. A stable termination property holds if and only if there is a stage graph proving it. But the really interesting thing is this one, that you can restrict yourselves, and this is a very deep theorem. The proof of this would be maybe 100 pages in total. Well, I don't know, not 100, depending on your level of detail, but a very serious thing. You can limit yourself to Pressburger stage graphs, where this means that the stages are Pressburger sets. So all stages can be defined by means of in Pressburger arithmetic. And the certificates, that's the important thing, the certificates are k-step Pressburger certificates. This means these are functions that are also expressible in Pressburger arithmetic. And moreover, since they are k-step, if I give you a Pressburger function, a Pressburger certificate, you can check it. Because for that, you only have to look in the radius of bounded size, which is not dependent on the number of birds or anything. So this gives you decidability. Okay, and this was proved in these two papers, but decidability is not the important thing, because, you know, yes, the problem is decidable, but the complexity is absolutely horrendous. The complexity is, you know, thanks to a recent paper, we know that the complexity is Ackermannian. You cannot do better than that in the worst case. The important thing is that this tells you, you don't have to go beyond Pressburger sets, and you don't have to go beyond k-step Pressburger certificates. So this means that the right ecosystem to conduct these proofs is an SMT prover able to deal with, you know, Pressburger arithmetic. But actually, you know, if you know a little bit about Pressburger arithmetic, you know that it admits quantifier elimination. So you only need linear constraints and modulo constraints. Okay. And of course, this gives you a lot of ideas for how to try to then construct the stage graphs. What you do is just limit your search for Pressburger stages and for Pressburger certificates to particularly simple Pressburger functions. Okay, you limit, for example, the I don't know, the length of the constraint or things like that. So how do we do this then in practice? So let me introduce this notion. A transition is dead at a configuration if no configuration reachable from it enables the transition. So this means that you will never be able to use this transition anymore, whatever happens. And then if you look at manual proofs, the milestones, the stages, right? The milestones towards getting trapped in post, they correspond to killing transitions. So the idea is that you show that eventually this transition is going to be dead. And then your new stage are the configurations where that transition is already dead. And then another transition will become dead, or more than one, and you proceed like this until eventually all transitions are dead, for example, or for example, the transitions that remain alive cannot change the consensus that has already been reached. So the automation strategy then consists of, given a stage C, find children stages C1, Cn, with strictly more dead transitions than C. So where more transitions have become dead. Okay? And you search for simple Pressburger certificates with the help of an SMT solver. So in fact, this is the general strategy. So you try to prove that S will eventually get trapped in the union of S1 to Sn. And notice that all of these have to be inductive sets, right? And how do you and these sets should have, these stages should have more dead transitions than the original one. So how do you do this? You start with S, and then you first have to you have a procedure which returns, if you are lucky, a set of transitions that will die almost surely from any configuration of S. Okay, so this procedure almost surely dead at S. If you are able to find some, then you compute an inductive envelope of the configurations of S at which the set of transitions you have already become dead. And this is going to be already the smaller set of configurations where you get trapped. Okay? But it can be the case that you don't find that. So it can be the case that, for example, it can be the case that this is your stage. And maybe there is no configuration that is going to become dead from all configurations. There is no transition, sorry, which is going to become dead eventually from every configuration in S. But maybe if you split S in a reasonable way, maybe you will see that T1 will become dead from any configuration on the left, and T2 will become dead from any configuration on the right. So then you split S trying to achieve this goal.
So Javier, you have about 3 minutes to wrap up.
Okay, good. So I just wanted to tell you a little bit about how to compute these inductive envelopes, right? And I want to mention that we use what is called, what I like to call actually the liquid abstraction, which is a notion which comes from continuous Petri nets, and is an abstraction which I think deserves more attention from the community. So, when I was a child, I liked this cartoon about 3 superheroes, and the one which is interesting here is Fluid Man, and which was the superpower of Fluid Man is that it could liquefy itself and then reconstitute itself at go somewhere and reconstitute itself. So now consider these transitions, which we can represent in terms of a Petri net here in the right. I think you will all see how this works. And now ask yourselves whether from the blue marking you can reach the red marking. And the answer is no, right? Because once after you execute, for example, this transition, then this token is going to stay there forever. You will not be able to move it. But if these tokens can liquefy, then it is possible to reach the red marking, okay? Because you can send, imagine that these blue tokens are liquid. So then you can send half a liter of liquid through that transition, half a liter here, and then you have half a liter here and still half a liter there. So you can now again execute this transition with half a liter and this transition with half a liter, and you see that you reach the final marking. So the liquid approximation, the liquid abstraction is an abstraction. The set of markings that you can reach, the set of configurations that you can reach with it is larger than the real one, but it turns out to work very, very well in practice. We base very many things on that. And the advantage is that the liquid reachability set of a Pressburger set is also Pressburger and computable in single exponential time. So that's all I wanted to say. Just apart from that, we have this nice tool that you can play with online, and that there are some experimental results that we don't have to worry very much about. Yes, if you want, keep this in mind, telling you that this is the typical size that we can achieve, for which we can do things, something like several dozens of states, several thousands of transitions, and that's it. Thank you. Now, while
thanks, Javier.
Yeah,
we have a question on the chat from Sanjeeva. So
right,
Sanjeeva, you want to pose it?
Right.
Javier, as always, a lovely talk. You know, this pre implies FG post is something that seems to come up so often in so many protocols, and
Right.
both in distributed systems, as you mentioned, and also in networks. I was just curious to see in how this idea of stages and this case step Pressburger certificate is a stronger method than, you know, what we've seen from you, for example, in VAS and using the Higman's lemma techniques to show that something converges?
It's not stronger. It is just basically stage graphs are a proof system, and the completeness of this proof system is guaranteed precisely by this result on basis. Okay. So, but of course, these results on basis, they are not, in practice, they are useless because they have a very high complexity. They explode in your face. If you are curious what I am showing you right now, what I am showing you is the protocol we have seen about the birds. And this is a tool that checks this the correctness of this protocol. Okay. And as you can see, it produces the stage graph automatically. Basically, what you see there on the screen is the stage graph I show you.
Yeah.
So by the way, this is the Boymo majority algorithm, and this game was actually the exact insight that led them to the algorithm. So
right.
Yeah. The algorithm was invented.
So I still think it's pretty impressive, right? I mean,
It is
while,
lovely.
while this happens in these few seconds, you are actually proving that an infinite set of Markov chains of arbitrary size, they all satisfy a property. So yeah, I think it's quite impressive.
So for this to kind of be more broadly useful, you need to create these multi-set abstractions of other systems. So have you looked at that, of extracting the kind of the termination core of
well, I mean, in fact, there is already quite a bit of work on that. So for example, I don't know if you know the work of Daniel Kroening and Thomas Wall and Daniel Kroening and Alexander Kaiser. So they have quite a few papers where they applied they apply these kind of abstractions to multi-threaded programs. So Jean-François has also some work on that. And of course, there is, where we are doing a lot of work is in this area of population protocols. I don't know if you are aware of it, but this is a quite active part of the distributed computing community now. So for example, last year it got the Dijkstra Prize. And those, you can put them directly here. There is also a community working on something called chemical reaction networks. Maybe you know the work of Luca Cardelli or people there. So those are already formulated as replicated systems, if you want. So there is no abstraction to be done there.
So the termination arguments, what is the quality of these? Are they do the sets that they give you, do they correspond to any kind of informal way that you might argue the termination?
I think so. well, it is. So in that sense, yes. So the stage graphs that we get are pretty small. So so let me see. There are two classes of protocols in the literature. There are the small ones where you can give directly a proof, okay, a manual proof. And for those, what we observe is that basically we always get automatically the corresponding proof. There are others which are the complicated ones where not even the description as they are not, in the papers, they are not described by giving the set of rules. They are described by using macros, right? So first we construct this little unit, and then we combine these two units in this way. It's not, you even have to do work in order to come up with a set of rules. And for those, we are very far away from being able to verify them or even give reasonable arguments. So
what do you get when it's not terminating? Sorry, finish your answer.
Well, okay, let me see. So for example, here you have a protocol where you only have 3 rules. You forgot the other one, which I told you is necessary for ties, right? So now if you try to verify it, let's see how long it takes. Right, so then you get a counterexample, okay? So you get a configuration from which you will not be able to terminate. And in fact, so right, you could now play it here. So in fact, you can, well, in this case, it is telling you, in this case, the counterexample is so simple that it is only one state, right? One transition. So initially you are now in S1, and then you go directly to S4, and S4 is not the right consensus.
Okay. So this can you do you have a link to this too that people can use?
Yes, I should. Okay. The tool is called Peregrine.
Any other questions while
if you go there, you will find there is a little demo, online demo, so you can start playing with it as I speak. But the demo will not allow you to verify. It will allow you to simulate and play with the protocols. If you download the code, then you will be able to verify. And you can download it from the same page, of course.
Excellent. Okay, Madhu has a question.
Are the stages produced by the tool expressible in logic succinctly? Well, that will depend, of course. I don't know, what can I show you? Let me see if I can show you something. For example, this is a protocol which was proposed by Alistair, by Alistair from in Austria. And here, I don't know. So let's see what happens if I verify it. I'm not sure how long this will take, right? As usual, when for the verification tool, I know that it not takes too long, but when you are giving a talk, 10 seconds, oh, it was pretty fast. So here, actually, you can see the description. I don't know. Okay, maybe you can see the constraint. So this is going, so what you see here is that this set of configurations is the set of configurations which are potentially reachable from this set of configurations. And what does that mean? This means that we apply the liquid abstraction. So this is the result of applying the liquid abstraction. The result of applying the liquid abstraction, it does not induce a blow up in the set of in the size of the constraints, right? But it could give you something that, of course, is then not so easy to handle by a human, right? That's I mean, if you want something that really you can see what it means, humans are very restricted, right? but it will not explode. That I can't tell you. And then if you move here, then it will be the set of potential reachable configurations from this one. So you can definitely read these things, right? They are readable by humans. And then you have, if you have a feeling, if you understand what this potential reachability means, you get a feeling as a human of what's happening there. But you know, you need this intuition about what this potential reachability means.
Thank you.
Okay. Thanks a lot, Javier.
Okay, thank you very much.
I'll thank all the speakers for their stimulating presentations. I'm going to pause the recording